Well, let's begin with the visioning workshop on carbon capture and sequestration planning for Southwestern Ontario for 2030. My name is Dick Jackson. I'm going to be your moderator today. And this meeting is hosted by the Waterloo Institute for Sustainable Energy and its new executive director, Claudio Canizares, will be welcoming you to the University of Waterloo. Claudio is the Hydro One endowed chair in the Department of Electrical Engineering, and Electrical and Computer Engineering, excuse me. So Claudio, please.
Thank you. Welcome to this workshop. It's a pleasure to be being here and a pleasure of seeing some people live for a change. I guess it's not quite a live event, but as close as we can get at this point. But thank you for being here, for attending. It's my pleasure to basically welcome you here and introduce you to our workshop. A few remarks before I start. This is me, which I was already introduced. I'm the new executive director of WISE, which is basically supporting this initiative with the help of our colleagues from the University of Waterloo. Before I get started, let me, before we get into the topic, let me introduce you briefly to WISE, what WISE is about. There are basically three major driving forces, if you will, of WISE, which is first, it's an institute which main objective is collaboration. So as you will see here, a mix of faculty members from different departments, different faculties make these, is what makes WISE. And we basically support all of those initiatives that we have, and as well, like this one. And certainly we certainly are very interested in collaboration with industry, which is one of the main motivations of this workshop. So we certainly have one of our driving forces reaching out to industry. An example is precisely this event, and and in that process was influence the decision-making process at different levels: academic, industry, and government. Now, these are basically the major topics or major areas that WISE covers. We cover all different aspects of sustainable energy systems in general. Conservation, improvement, transformation, other aspects, technology aspects of policy, technology, aspects of energy systems, and certainly the delivery of it. In my personal expertise, I'm from the power system side of things. I work in power, in the power grid, and we in my area, I one way or another I participate in all of these different aspects of the scope of WISE. Now, these are the colleagues who have basically made this possible, who have set up created this idea and set up this event, from which I'm very supportive and appreciative. Some of you, I guess most of you know all of them. We have Maurice, Richard. You can raise your hands in case they haven't seen you. Maurice, Richard, which you already met. We have Roydon Fraser, which is sitting here, Eric Rosette, and myself. And certainly I have to recognize the staff that made this possible, Armugan, and I guess most of you met Sana, which is sitting outside, which are basically the staff that from WISE that has basically organized with the help of the colleagues from I've already introduced, make this event. Now, what is the motivation? What is the motivation of this event? Or what brought us here? So one of the main issues that, as you all of you are aware of, is the federal government commitments as of 2030 and going beyond that 2050, which is net zero, right? So that's basically driving through federal carbon tax policies, driving these force towards a no-emission system. Now, the challenge with that is, right, that industry is facing a major challenge in this process. Because certainly the industry is vulnerable to this transition to low carbon, especially by in the midterm and in the short term and in the midterm, right? We're talking about in a few years, basically, I guess 30 years to 2050, 10 years to 2030, which is certainly quite immediate. And in that sense, the intention of these, which is part of, by the way, is part of the Sustainable Development Goals of the UN, which basically cover all of these different aspects. This particular event touches these different aspects of SDGs. And in that regard, okay, the intention of the workshop, the goals of this work, the objectives of this work, which I'll revisit later on in my closing remarks, is that we establish an industry, academic, government collaboration, okay, all across the board, to adopt basically, because carbon capture is going to have to be part of the solution, especially in the short term and midterm, and basically appraise the perspective of sequestration sites. That's the objective of this event, and the use of energy efficient technologies. So throughout the day, we'll have this discussion. We'll have these presentations, basically addressing all these different aspects of carbon capture in our path to net zero by 2050. Now, in the process, or the other objective of this event, as I already mentioned, is to basically establish this collaboration from the point of view of R&D, okay? And also, the other objective of this, being a university as we are, the institute, is basically the training of people, the highly qualified personnel, okay? So part of the objective of this, through hopefully collaborations, contracts, grants that we hope come up of this event in the short term, would be also training, not only research and development, but also training of our people. And looking forward at the possibility of pilot scale test facilities as part of the R&D and HQP objectives of WISE, University of Waterloo, and in particular this event. With that said, I think that our next, I only have 5 minutes, which I think I already took for this introduction. And our next, let me look at the agenda here. Sorry. Oh, here it is. Yeah. So I guess Richard will take over from here. Go ahead, Richard.
Thank you, Claudio. Our next speaker, who is giving the keynote speak today, is Drew Leyburn, Assistant Deputy Minister of the Energy Technology Centre in Natural Resources Canada. Now, of course, Drew Leyburn actually got a new boss yesterday, so we're particularly fortunate to have him with us today. Before he became ADM in the Energy Technology Centre, he held various positions as Director General within NRCan, Natural Resources Canada. And prior to that, had worked with McKinsey and Company. Prior to that, he'd been an undergraduate at Bishop's and became a Rhodes Scholar at Oxford. He actually grew up on the shores of Lake Erie, which gives some relevance today. NRCan's energy technology sector supports the advancement of clean energy technologies through R&D, and Drew Leyburn has responsibility for directing the CanMet labs in Varennes, Quebec, opposite, on the South Shore, opposite Montreal, in Ottawa and in Hamilton, and also out in Devon, Alberta. These drive the development and demonstration of clean energy technologies and advanced materials to support the government objectives and priorities, with the ultimate goal of lower carbon economy, both domestically and internationally. So from Ottawa, I trust we can bring in Drew Leyburn.
Just want to check that you can hear me okay. I think I heard myself on feedback there, so I think we're good to go. I'm really happy to be here today. I wanted to start by noting that I'm joining you from the unceded territory of the Algonquin Anishinaabe Nation, and I encourage each of you to take a moment to think about the land you are on and its history. And I'm here in my capacity, particularly as the lead responsible for developing a CCS strategy for Canada, which was launched in the federal budget earlier this year. So much of my commentary is going to have a national bent, but a really important role for any national strategy is making it clear that CCUS's promise is pan-Canadian. It's not just one region or one industry or one application that can benefit from this growing and really necessary industry. So the CCS strategy will need to make sure it's drawing out those regional stories. And so I'm particularly happy to be talking about that opportunity in Southwestern Ontario. As Dick noted, I grew up on the shores of Lake Erie, and actually my mom's from St. Mary's. So at a minimum, I'll be making sure that next time in all the documents, the apostrophes are removed from St. Mary's Cement. The other thing I'll briefly mention, and it was acknowledged this morning, Natural Resource Canada got a new minister yesterday, Jonathan Wilkinson. He's just settling in, and we've not yet had the chance to get his personal thoughts on CCUS. So today, while we're still in a kind of political caretaker mode, I'll be speaking in general terms, and nothing I say should be interpreted as what the next political mandate might take us to. So maybe I'll just briefly spend a few minutes then talking about, why CCUS is so important for Canada and for the world. It is an area of significant opportunity for Canada and an essential part of our transition to a net zero economy. I like to say that CCUS is the biggest difference between a net zero carbon economy and a zero carbon economy. And so it will play a crucial role, particularly for countries like Canada with the industrial base we have. But globally, to reach net zero by 2050, the International Energy Agency estimates that CCUS will contribute about 15% of GHG reductions, and that without CCUS, the cost of reaching net zero globally will increase by about $15 trillion. So as I said, Canada is well positioned to be a global leader here. It offers the opportunity to decarbonize today's emitters and reduce the cost curve for the remaining emitters in 2050. When I talk about Canada's advantage, there's a few things that come to mind. I like to call them the 4 E's. So the first is history, ability, geology, and policy. So on the history side, we've got 30 plus years of CCUS, RD&D, and practical experience in the form of projects. 4 of the world's 25 large-scale CCUS projects are in Canada, and the work of federal and other labs across the country have been kind of at the vanguard, including universities, for the better part of 30 years when it wasn't called CCUS, but some of the work we were doing around abating emissions from coal, for example, in the 80s and 90s has borne fruit in other industries. On the ability side, we've got cutting edge tech developers and adopters. We've got expertise from various sectors, including oil and gas, which is portable and can be used, I think, to further this still kind of fledgling industry. We've got those big projects I mentioned, but we also have a good proportion of the major players in the U part of CCUS, so the carbon utilization side, companies like CarbonCure and Carbocrete and others who are finding novel ways to use those carbon streams once they're captured. And of course, we're also leaders in the segment of CCUS, which is direct air capture. And so companies like Carbon Engineering are, one of a handful, truly a handful of companies that are pushing the limits in that space. On the geology side, we have a huge amount of pore space compared to almost any country in the world. 70% of large emitters in Canada are co-located nearby abundant storage potential. I know that's going to be a big part of the discussion today as it pertains to Southern Ontario. And on the policy side, we've got a lot of the pieces in place that make CCUS more attractive. We've got a predictable carbon pricing regime, which by the end of this decade will push carbon prices into a zone where a lot of CCUS projects come in at a cost lower than that carbon price. We have an investment tax credit pending. My colleagues at Finance Canada have been working on that over the last few months for release in 2022, which will, through the tax system, encourage more investment in CCUS. We've got a clean fuel standard, which also incents CCUS and as a pathway to cleaner fuel production. And we also have provincial frameworks across the country that have really been doing a good job at lowering the barriers to entry for CCUS. So most recently in Alberta, for example, a new regime that encourages the creation of CCUS hubs and kind of eliminating the Wild West aspect of ownership of pore space. We've got provinces like Saskatchewan and others that are looking at similar regimes and how to unitize and make fair the carbon regime for storage and transportation. And we also have program funding. So most recently, for example, the $319 million that my department, Natural Resource Canada, was given to deliver CCUS RD&D across the country. There are still challenges for CCUS, some global, some national, and some local, and I think the local ones in particular we'll be discussing today. But we know that despite all the policies that we have in place that make CCUS, Canada a CCUS-friendly place, we know there are other jurisdictions that are looking to outcompete us in that space. So, Norway, UK, definitely a kind of friendly competition with them, with the US and the introduction of 45Q, which is their tax measure. We've seen a huge increase in CCUS activity there, and that's something we're very aware of. We know that the cost of CCUS need to come down for it to fulfill the role it needs to in our climate mitigation story, notably for capture. But obviously in new areas where geological sequestration or storage is being undertaken for the first time, there's also cost curves that need to come down there, transportation costs, et cetera. On the issue of transportation, we know that you need infrastructure. The concept of CCUS hubs, I think, is really taking hold. And while there will be kind of one-off CCUS projects in various places around the country, I think the biggest winners will be in those areas where you can create a multi-client, possibly multi-destination CCUS hub. But they are capital intensive, and the future demand for capture facilities can sometimes be uncertain, particularly on the use side. There's also outstanding technical and commercial risks. So, there are difficulties in allocating risks amongst project partners, which can sometimes impede financing and investment. Our colleague Peter Trzakian in the energy space frequently says that if we're building a CCUS industry, we need to make sure that there's a way that every part of that value chain can make money, not just the carbon producers, not just the capture units, but also the storage people, the transportation people, and the service companies in between. But there are also additional risks, which I think have been identified in some of the in some of the pre-reading that was distributed in advance. Those include some geo risks that I think we're still getting a full handle on, but we do have now 20 plus years, 30 years in places like Norway of demonstrating that geological storage is safe. But other things just generally that don't even have to do with CCUS sometimes, but the natural gas infrastructure that may play into a CCUS project. We know that it's not completely airtight, that there are still fugitive and other emissions that would need to be addressed for this to be a truly net zero technology. So maybe I'll wrap it up by just saying that, as part of our strategy that's under development, we're trying to identify the various pathways that CCUS can play in a net zero decarbonization strategy. The first is cleaning up heavy industries, particularly those industries that have kind of unavoidable emissions. We know that CCUS is going to play an important role for low carbon hydrogen, and particular blue hydrogen in particular, that's derived from natural gas sources. We know that CCUS will play a crucial role in Canada in cleaning up the oil and gas sector and reducing the emissions on the production side there. There's a potential role for decarbonized dispatchable power when you bring in CCUS. There's negative emissions for carbon removal, which I think is going to take on an increasingly important role as we get closer and closer to 2050 and even 2030. And then there's also CO2-based industries. So I mentioned a few of those companies in Canada, but I think you are going to see an increasing attention on some of the useful carbon products and additives that can be derived from that hydrocarbon or other CO2 derived base. So I'll wrap it up there. As I said, the strategy is still under development. Once our cabinet settles and we've got a better sense of the mandate letters and where this government in its current form wants to go with CCUS, we'll start reopening some of the conversation about that strategy itself, and with a plan that over the next few months, Canadians and stakeholders would start to see the fruits of that drafting. So I'll end it there. I think I'm at about 15 minutes, and just say thanks again for all of your work today.
Well, that was just excellent. That was a splendid introduction to the problems that are in front of us. We'll now proceed with the program. What we're going to start with is Royden Fraser, Professor of Mechanical Engineering, and Maurice Dussault, Professor of Geological Engineering, are going to give us a briefing on the major technical issues as we see them here on campus. And then I'll be introducing Alexandre Rougier from the Canadian Steel Producers Association and Hilary Thompson from Enbridge. So first of all, Maurice and Royden.
Well, good morning. Very pleased that all the attendees here. This presentation by Maurice and myself discussing the problems, it's going to be pretty succinct. Many of you are going to know your area, maybe some of the other areas you don't know as well. We're going to go through this fairly quickly. There's quite a few problems and challenges to identify. So to start, we need to meet Canada's 2030 emissions targets. There is the jobs in Ontario, where Ontario focused with this particular workshop, and help decarbonize Ontario. Heavy industry is also one of the aspects of the challenges. Essentially, capture, transport, and storage. The workshop priorities or premise here is as follows. Whoops, I think I went too far. Here we go. Workshop premise, we need decarbonization in Ontario quickly. We're approaching 2022, 2030 is only 8 years away. Used to feel like 10 years. It's going pretty fast. Southwestern Ontario's sedimentary basin offers some capacity for CO2 sequestration. And our intent here is to help industry with the transition to that net zero future. The massive sequestration in Ontario can only exist for a limited time. We only do have a limited capacity, so 10 to 15 years. Likely is what we have here if it's a very massive use of our available storage, but we don't actually know how much storage there is, and that's one of the challenges. We're going to try to meet the 2030 goals of the federal government, and all at a reasonable cost. We know the economics plays a huge role in what choices are going to be going forward with reducing carbon. And we're under the premise that alternatives are not attractive, but we do know there are alternatives, and in the discussions this afternoon, hopefully some of those alternatives will be discussed. So, with regard to the sort of big three domains of capture, transport, and storage, we only have secure storage for a limited amount, but we want it to be for an indefinite time, right? And large volumes involved. Okay, so reasonable time and large volumes. And there's our three main considerations, and then just another graphic with the three main considerations, a little more diagrammatic of the capture, transport, and storage. And so I'm going to go into a couple of the challenges. I'm going to start with the capture, and then Marisa will take over, and transport, and Marisa will take over with sequestration, like the main focus of today's conference. So CO2 capture, we have the methane oxy-combustion. We can use that. That'll give us a fairly pure carbon dioxide flow. We can intercept flue gases, which will have a lot of nitrogen and CO2 in it, and then we have to purify that. To what percentage level is going to be needed to purify? Put down here 97%, greater than 97, question mark there, but we'll purify it. And large amounts, megatons per year, we're talking, reasonable costs, and has to be reliable and work. So, just as an example, this is just one example, it's not all the examples. With cement kilns, you have the CO2 from the hydrocarbon fuel that's used, say methane, the combustion that you have, and you also have it from the calcining process. So cement industry has CO2 considerations, and there's alternatives to how to deal with that, maybe a change in technology, or sequestration is one of the alternatives. So that's the capture side. It'll be given in more detail. Eric Wisset later will give a presentation in more detail on the capture side. With regard to transportation, we have emission sites are not sequestration sites. So the two are not the same location. We need hubs of local storage at both the sequestration sites and the capture sites. So not just the pipeline in between, but also local storage. In Southwestern Ontario, we have some methane pipelines already, so it's possible, for example, that you have slugs of CO2 going through those existing pipelines, or there may be the need for a new trunk line like the Alberta carbon trunk line model. Now, in case of timing, I'm going to skip over the next slide, which just talks about the Alberta trunk line, and pass this over to Maurice to talk about sequestration.
Thank you. The capture, transport, sequestration, actually, in terms of the science and engineering, has to be flipped around. We must have sufficient storage for the sequestration before we invest dramatically in the capture and transportation sectors. We need adequate capacity, megatons per year for a 10 to 15 year transition period. And when I say 10-year life, I mean 10-year injection life. These sites must be secure for much longer than that in terms of escape. We have depleted gas and oil fields in Ontario. Some, the deeper ones, may be suitable. One nice thing about a depleted gas field, it's an empty bottle. We can actually fill it. If the pressure is very low right now, that means we have a lot of capacity to fill it. But most of them are saline aquifers, and that means that the water has to be displaced. Many technical issues arise. I'll discuss some of these at about 11:30. Okay. So, as an example, amongst many, we see here the contours of the Cambrian Formations, the deepest ones in Ontario. And we are studying the Cambrian Formations as potential repositories because they are the deepest and they do have some pore space, usually filled with brine. And we have to bring it all together seamlessly, of course. So, there we go, yes. So here are some of the sites. The little colored squares are the large emitters. And I just drew some yellow stars to say maybe this is potential array of hubs for capture to create a suitable 97% CO2 stream for sequestration. Okay, so we have the hubs, and we have the potential, and this is entirely figurative here. There is no guarantee that these are good sites. The sites for sequestration, and of course, these sites have to be linked with appropriate transportation. So, in conclusion, before we focus on capture and transport, we have to make sure that we have the sufficient pore space to sequester the carbon dioxide. And that means a bunch of geomechanical issues such as cap rock integrity, pressures, temperatures, legacy well sealing. And our conceptual Ontario trunk line, ONTL, that I showed you, it's basically, I believe, personally, Enbridge may correct me, but I believe that we actually have it in large, maybe 90% of it is there because of the existing network that exists in Ontario that could be dual-purposed. And the bottom line says we have to meet a deadline for the beginning of injection by essentially 2029. Tempus fugits. Thank you.
Our next speaker is Alexandra Rougier, who is director of the Canadian Steel Products Association. And she's going to give us a briefing on their work on carbon capture and sequestration.
Thank you. Thank you very much. Good morning, everyone. I'll just get myself settled. Again, on behalf of the Canadian Steel Producers Association, thank you very much for the opportunity to join this morning. We are very excited that what we had projected to be a 2040, give or take, technology support for our sector's decarbonization is already being engaged very actively right now. This is a very exciting time for the sector. It goes to support a lot of the federal government's goals that we are seeing aggressively timelined, with the latest NDC going up to 40 to 45% reduction by 2030 across Canada. And as a hard-to-abate sector, those are very concerning targets, partially because the technology, unfortunately, to support our transition is not readily available, it's not accessible, and it's not economic. So I really appreciate the ADM's comments this morning addressing, the feasibility and the economic piece of CCUS. But that being said, I am by no means a geological engineer. I'll leave that to the specialists to develop. And really the purpose of me being here today is just to support a bit of a sector overview of who we are, where we're located, and really just in part the fact that the steel sector is of heavy emissions intensive industry, but we do have the potential to be one of the main key players and supporting players in a lot of this hub concept, and are keen to work with various stakeholders to be able to realize those goals. As a sector, we're located across 5 provinces in Canada. Most of our heaviest emitting operations are located here in Ontario, 2 of which are located in Hamilton. One is on the shores of Lake Erie, and the other is Algoma up in Sault Ste. Marie. So the particular scope of this conference today is of keen interest not only to our mills located here in Southwestern Ontario, but also the entire broader sector. Because as I mentioned earlier, we really do have the capacity for this to be kind of our first learning step in developing CCUS and applying it for our use. Just some metrics to give us some scope. We are a $15 billion industry. We do support hundreds of thousands of jobs across Canada. And we are key in the North American market. And for this reason, we do obviously support the continued improvement and decarbonization of our sector here domestically. For those unfamiliar with the steel sector, there are presently 3 main processes for actually producing steel. The first one is the most carbon-intensive process. So it incorporates the use of a blast furnace to reduce the iron, as well as coke-making operations to actually provide that carbon to make the reduction possible. And then the final step within that process is the basic oxygen furnace. So that's where all of the products come together, you melt the steel, and at the end of the day, it's cast. The second operation actually doesn't occur yet in Ontario at this point in time. There are plans in development for one of our facilities. However, in Quebec, they do have a natural gas-driven direct reduced iron system that is at ArcelorMittal Long Products in Quebec. And essentially, they reduce their iron through a different process, not through the blast furnace route, through the DRI, and then it's an electric arc furnace that does the final melt precasting. The last route, which is the third one shown here, really has the capacity to be based on 100% scrap steel. So these are our mini mill or our EAF facilities. They're located throughout Canada. Actually, each province has a few of them. And really, this, like I said, has the capacity up to 100% scrap being used. But an important message, I think, for all of these operations are, really they're organized, in levels of emissions intensity, but it is important to note that no matter what, the cleanest operation that we have available to us with the technology and the fuel sources available, there are still fixed process emissions that remain. And these fixed process emissions are something that even if you have the most aggressive technology in place, you still have emissions that you cannot abate at this point in time, which is why as a sector, no matter what, for all of our operations, we do see carbon capture as being one of the many ways we will need to decarbonize by 2050. To provide you with a scope of the emissions and the level of emissions we have across our Ontario facilities, as I mentioned, ArcelorMittal Dofasco is located in Hamilton. So they, based on 2019 GHGRP reports, they are the highest emitting operation here in the province. The second highest emitting is Algoma in Sault Ste. Marie, and the third is the combination of Stelco's operations located both in Nanticoke and in Hamilton, Ontario. So those 3 operations are the integrated. You can see the scope of the emissions are between 3 and 4 million tons. And it's important to note that for those who are unaware, actually, the Net Zero Accelerator Fund recently funded both ArcelorMittal Dofasco and Algoma Steel with transformative funding to be able to achieve the implementation of new technology. The important thing to note here that is with even that technology implementation, which will take their emissions, say, from 4 to a total of 1 million tons, there are still 1 million tons that will need to be abated no matter what. And this will be, we can forecast this for the future up until 2050, really, which is why, again, reaffirming the fact that we do need carbon sequestration as a transformative pathway. In the Canadian context, we are a heavy hitter as well. We're about 2% of Canada's total emissions and about 8% of Ontario's specific emissions. We recognize the importance of addressing carbon emissions and transforming into the low carbon economy. Never mind our emissions, this is actually a mandate that all of our member companies feel quite strongly about, which is why in 2020, so coming up to 2 years actually, we published our first climate call to action. This was a collective effort signed on by all Canadian steel producers across Canada, and it was really the group of them coming together to sign on to an aspirational goal. I think the key word here is aspirational. We appreciate there's many technologies that are still in development, that need to be deployable before we can achieve anything. But that being said, it is an aspiration. It is something that as a collective we are supportive of, which is really why we're looking to continue to support the work that's being done here today. It may be for a specific portion of our sector here in Southwestern Ontario, but that being said, the lessons learned will have gross application across Canada. So as I had indicated, our goals do align with the federal goals. We don't have an interim target at this point in time, but that being said, if we have carbon sequestration by 2029 available, this has a huge opportunity to be able to bump up exactly how we get to our final aspirational target and the timeline within which we do. Within the climate call to action, we really established all the conditions for success that we will need as a collective to be able to reach decarbonization. This is not unlike any of the federal government's goals. I mean, every sector across Canada really needs a combination of collaboration, research, stakeholder interest, continued improved operational excellence, things like that to maintain the wheel and to be able to put themselves in a position to decarbonize. And I think the other important thing is Canada does have the capacity to be a global leader in this space. As the ADM had mentioned, we do have the geological benefit, I guess you can say, of having very porous geology. So this is just one of the ways in which we can aspire and continue to be global leaders. As a sector, we identified several key places of technology development that we need. Obviously, carbon capture, storage, and utilization are one of our key methods to be able to reach our decarbonization goals. But the bottom line is, and I would like to complement a lot of the comments that have already been made, is that there will be, we will need a collective effort, and we will also need a multitude of technologies available. The decarbonization strategy is really across all facets, whether it's hydrogen or CCS or a biomass use, increased green electrification. All of these pieces need to be working together in motion to be able to facilitate the decarbonization. We already have a very strong standing relationship with CanMet Labs in Ottawa. So the Canadian Carbonization Research Association is one of our, I'd refer to them as our research arm, that supports our sector in doing a lot of the deep technology and research work that have been driving all of our improvements, many of our improvements really to date. At the end of 2020, we took to kind of creating a placemat. And this really, the point of this, I don't think anyone can read the fine print. The point of this really is just to show the multitude of technologies that will be established, that we will need to be established to be able to drive where we are going as a sector and how we hope to support Canada in their decarbonization. Bottom line, innovation continues to be the most pivotal aspect of our goals to decarbonize. The value chain, the significant markets that need to be developed, and really the technologies that need to be ready to be made to be deployable are the key limiting factors to be able to reach our net zero goal. As an essential material that, steel as a material can be recycled infinitely, we see its capacity, we see its requirement in the market to actually increase by up to 30% as we continue to decarbonize. It will continue to be required as our society transitions into this new economy. And for this reason, we really do see that we want to ensure the competitive advantage of the steel sector within this transition. We play a key role in addressing global CO2 emissions, the provincial emissions, as well as the federal emissions. And we're really looking to work with all aspects, all partners and stakeholders to be able to facilitate these technologies. We are very proud to say that as a Canadian sector, we have the advantage that internationally we are actually already quite green. This was actually a study, not biased, it was done by an American organization actually. And it really goes to show that, because of the combination of, green electricity or access to green electricity, the level of environmental regulation we have on our operations, the technologies we have in place, the continuous improvements that our membership does, we are already in a position to be some of the world's greenest steel produced. And I think for this reason as well, we want to ensure that we maintain and promote and continue to drive the development of green steel here in Canada. Given Canada's climate leadership, the country must develop kind of all of the enabling policies, and again, the ADM did flag a lot of those: the CCS strategy, the tax investment credit, the net zero accelerator, all of these government funding opportunities, as well as the specific $319 million that is dedicated to CCUS specifically. They need to work together to be able to collectively strategize and support the decarbonization of not only the steel sector, but really all of our intensive industries here. So on behalf of all of the members of the CSPA, thank you again for the opportunity to present to you today and give you an overview of our sector, where we are, where we're hoping to go. I think, again, bottom line, we do want to we do want to take this opportunity to say that this is very important to us, and not only for our steel operations here in Southwestern Ontario, but also the collective industry as a whole. We're very keen to work with all of our stakeholders and a group of gentlemen who have already initiated this work. And I guess that's it. Thank you again.
Thank you, Alexandra. Those of us who have lived at one time or another in our lives in Hamilton appreciate what is happening there. And we do hope for the continued sustainability of Canadian steel industry. Our next speaker is Hilary Thompson. Hilary is a chemical engineering graduate from Queen's University, following which she obtained a law degree. She is Director of Science and Technology within Enbridge Gas and is based in Toronto. Hilary will talk to us about Enbridge's natural gas storage and transportation system, which is tremendously important, really, because it shows that we know how to store gas safely in Ontario, and we know how to transport it safely. So that bodes well for carbon dioxide storage and transportation.
Good morning, everyone. Thank you so much for the invitation to speak here on behalf of Enbridge. As Richard mentioned, my name is Hilary Thompson. I'm the Director of Storage and Transportation Business Development at Enbridge Gas. And while I'm on intros, I'd like to take the opportunity to introduce my colleagues within the room. Steve Party, we're spread out, Jeff Cadott, Matt Thomas, and Wayne Passmore. So the five of us here will be your primary contacts, and we look forward to connecting with you. In relation to myself, unfortunately, I'm not able to stay for the whole day. I do have to leave right after speaking here, but I do look forward to connecting with you in the future, and it's so nice to see everybody here in person. So as mentioned, I'm here to talk about Enbridge Gas, our core business in storage and transportation. And Steve Party later today will get into further detail on our storage assets. Okay, a little bit about Enbridge Gas. For those of you who are not familiar with us, we serve the 5th largest population in North America. We serve 75% of Ontario's population overall. That includes 3.8 million connections. And we have the 2nd largest storage hub in North America. Overall, we are the largest utility by volume. So we serve many of the markets that you see here highlighted in yellow on the screen. And beyond that, we also serve markets in and around the Great Lakes on both sides of the Canadian-US border, as well as further to the east in Eastern Canada and the Northeast US. So because of our experience, we have a lot of expertise within distribution, transportation, and storage within Ontario and across the North American province based on the other areas of operation for our liquids and gas assets. So on that note, I do want to mention that we are one operating division, and we do have quite a bit of work going on across the company that I'll speak to a little later in the presentation. Okay, so as mentioned earlier today, it's actually very exciting to hear that without even having a session like this to this point, that a lot of us are communicating the same messages and we're thinking in the same way, and there's a lot of passion behind the objective and what we're trying to do here. And I know that it was already mentioned as well that we seem to be accelerating, that the vision for CCUS in Ontario was projected to be a little bit further out, but really we've picked up a lot of momentum over this past year. And as a result of that, and really as a result of the impacts of the pandemic, we're seeing a lot of messages out within the media being produced by different companies and different agencies, and really there's a lot of confusion around what that future will look like. And of course, there is a lot to determine, and we know a lot about what the short term will look like, but we are still trying to understand what that long-term view will look like. And one of the important parts of us coming together here today and continuing to come together in the future is getting that alignment so we can continue to share our perspectives, come together between industry, academia, and the government in order to really support each other in building that path forward, particularly for Southwestern Ontario here. Another way that we can really keep a good connection on building that path forward is really understanding the wants and needs of the customers, which includes residents, our commercial customers, as well as our industry partners, which is really the key component of supporting CCUS for Ontario. So on that note of having differences of perspectives, I don't know about you, but I have heard many different perspectives out in the media around what that future looks like. So I thought I would take a minute to just talk about the future. On the slide that you see here, we have two graphs. On the left is the Canadian projection of natural gas demand out into 2050, and on the right, it's the projection for the US. I know some media outlets and different partners really report a lower projection, but when you look at the bigger context of energy demand in North America, we continue to see that natural gas will continue to play a very important role going out into the future, all the way to 2050. And for that reason, we have to continue to look at these solutions such as CCUS in order to support the continued use, in order to drive towards that net zero target. So why is that? Why are we continuing to see the continued use of natural gas? And in some cases, the increasing use of natural gas. And there is a couple of important factors. For Canada and in Ontario specifically, natural gas is 75% of the heat and space heating load. It is 30%, or 36%, excuse me, for the industrial load, and it's expected to grow over time. And that is a key aspect. The reason why it's expected to grow over time is because our industrial customers will be shifting their energy demand from different types of hydrocarbons and shifting towards the use of natural gas. So this puts further emphasis on the importance of CCUS. The second part, which is in the middle of the slide, is the reliability. The peak natural gas demand in the winter is 3 times the electricity peak. And to generate that much electricity, we would need to build up to 90 nuclear reactors in Ontario alone. So now think about that from the national perspective and even the North American perspective of what that would actually look like. We need to be thinking about all these considerations. And lastly, from a cost perspective, of course, affordability is incredibly important to all different types of customers and all different types of residents and businesses as we move forward. So between these 3 factors, it is extremely important that we continue to work together in order to find the solutions that suit the need to continue to make our energy affordable and reliable going forward. What you see behind me is a schematic of the Enbridge Gas Area, and I just wanted to take a minute just to mention it, especially with respect to some of the other maps that have been showed earlier today with a mapping of the industrial customers. You'll see that the geographic area that's showing here, we have natural gas assets all over Southwestern Ontario. So we are looking towards really understanding what the particular needs are of our customers and looking at the asset footprint that we have to date in order to make sure that we are taking a thoughtful approach and making sure that we strategically plan to support our customers both for the short and long term. From the storage perspective, Steve will be speaking more about that later this morning or this afternoon. So the future of Enbridge, we have been giving a lot of thought to what that may look like. On the slide you'll see behind me, we have the different operating divisions of Enbridge and the different considerations that are being made both to support our core business and also to support our existing and future customers going forward as it relates to lower carbon growth. We are going to continue to make sure that we focus on the ongoing safe and reliable operations of our natural gas system as well as our other operating areas. And we are going to strive to optimize, expand the assets where needed in order to serve that growing demand that we're seeing for projections going forward. And we're also looking at greening our operations. So CCUS may also play an important role for the operations as well. On the right-hand side of the screen, you'll see that we are looking into all different areas across the business: RNG, hydrogen, CCUS, and more. And one of the great aspects of having the different operating units look at all these different types of technologies and opportunities is that we're able to explore opportunities all over North America and really lean on each other and learn from one another to support the development both within Southwestern Ontario but across North America overall. And as mentioned earlier as well, we really do have a great opportunity to be a global leader within the space of CCUS. And we are really looking forward to continuing to build those relationships with our customers, with academia, with industry partners, as well as with the government in order to make sure that we do what we can to enable CCUS going forward. So just a couple points further to add is that we do have a number of other different types of solutions that we are going to be looking at. And We just highlighted a few here. So we're looking at all different areas. So anything from our demand side and also our supply side for alternatives. Okay, and lastly, as mentioned, we will continue to support that ongoing growth. We will continue to support the development in future opportunities and to allow us to move forward towards that lower carbon demand. And what you see on the map on the right-hand side is that mapping of these different opportunities coming together. And hopefully over the course of the day, that's going to be part of the discussion as well, is really looking at the assets that we have to date, the industrial customers and other types of customers that we have within Southwestern Ontario, and how we can each come together to really support that lower carbon future. Okay, thank you so much, and I look forward to connecting with you in the future.
Now we're going to talk about carbon dioxide processing for sequestration and transportation. Our first speaker will be the head of the Department of Chemical Engineering, Eric Croiset, who will be speaking on process engineering, something he's been working with CanMet on for many years. Eric?
Okay, so good morning. So I'm very happy to be here to talk to you about some about carbon capture. But by the way, Richard, I'm no longer the chair of the department, so now I can do these kind of things. So my presentation called Process Engineering Fundamentals for Carbon Capture is actually more a very brief introduction to carbon capture. I understand the focus is more on storage, but let's not keep track of, forget about the carbon capture part. Okay, I'm going to skip quickly this one, but the carbon capture is the most expensive part of the capture, transport, and storage, so that's why it's requires a lot of attention. So, there are many ways you can capture CO2 from a stationary source. Here it's a classic representation of those different ways. So we have post-combustion, pre-combustion, oxy-fuel. I guess here in this graph you have industrial processes, which is more relevant to what we are talking about today, but in a sense they follow very much the above. So post-combustion, as the name implies, you don't change anything on your process and you just treat the flue gas. Pre-combustion, I'm not going to dwell too much. This is more for the power sector, but basically it's you gasify and you separate the CO2 before, let's say, you burn the hydrogen that came from the gasifications. In the post-combustion, essentially the separation is to separate CO2 from nitrogen. That's from a combustion process. That's essentially what you are doing mostly. In oxy-fuel, the idea is to remove the nitrogen upstream. So we need an air separation, and we burn the fuel with oxygen. Well, we might have to do a little something I'm going to talk about briefly to control the temperature, though. So now I'm going to look quickly about post-combustion capture and oxy-fuel, and I'm going to present also another one. Oh, it didn't change here. Okay. So on post-combustion capture, there are different ways you can do that. You can use a chemical solvent. which is currently the preferred choice, and I guess the base, everything is compared to that process. You can use physical solvent, which is suitable for high-pressure system. So this is not really often the case in the processes we're dealing here. You could have adsorptions, like PSA, pressure swing absorptions, or TSA, temperature swing adsorptions. You can use membrane, or you can even use low temperature distillation or flash. So those are the different options possible. So since the solvent is the base case, everything is compared to this one, I'm going to focus a little bit more on that particular one. So it's a mature technology, which is a good thing when you want to build, although the scale is a little different from the usual applications. So basically the way it works, on the left, so I can use a laser for people in the audience, but I try to explain sufficiently clearly for those who are remote. So on the left, we have an absorber column where the flue gas is basically put in contact with the solvent. The solvent is capturing the CO2. On top of that absorber column, then we have a CO2 depleted air that is vented. On the bottom of the column, then we have the solvent with the CO2 in it. Then it goes to another column. It's a regenerator column where you do the opposite, where you separate the CO2 from the solvent. The CO2 is then, basically that's the CO2 you have captured, and the regenerated solvent is sent back to the absorber. The way we regenerate the solvent is through bringing some heat in the so-called reboiler on the right. And this is pretty much where the operating cost is. This is a big energy penalty of this process. So if you have some waste heat available, that will be perfect. You can probably, that could help a lot. Now, when we look at chemical solvent, there are several you can use. Ideally, you want a solvent that has high CO2 loading, so you can capture a lot of CO2, and a low energy of regenerations. I mean, life is not perfect, and this is difficult to find these. The so-called aqueous amine solvent are the most common. The one has been used for decades, like MEA, DA. There's a lot of work, research work and development work for other solvents, like some of those you can see here. And we have to keep in mind that impurity in the flue gas needs to be dealt with, and there may be some corrosion issues. We may limit the amount of your solvent also. So that's some constraint associated with this process. So here, I have a picture of a real plant. So there are very few big ones you can see. I would have loved to show a picture of Boundary Dam. I could have, because that's a Canadian one. But this one is from the so-called the Petranova plant, coal power plant in Texas. And I choose this picture because we can see a little better how things look like. So the capture plant, so this is a fairly big power plant here. I forgot exactly, it's more than 600 megawatt power plant. And the capture plant is really these things here, where you see carbon capture facilities. And this one, you can see on the right, you've got the flue gas duct that comes from this unit to the capture plant. And if I'm not mistaken, the size, so you can have an idea of the size. And the size here is maybe for about equivalent to 240 megawatt plant. So that gives you an idea of the size. So the big column you can see where it's written carbon capture facility, it's the absorber I showed you in a previous slide. And there is a smaller column on its left. This is a regenerator column. you can see, I mean, here, I would say at the bottom of the absorber column, a little in front, this is actually the CO2 compressor. By the way, this CO2 capture plant is to send CO2 about 80 miles away for enhanced oil recovery. That's where it has been used. Something interesting to notice in this one, I told you we need to bring a lot of heat in this system. There is a dedicated cold generation plant for the capture plant. Yeah. So now let me talk about oxy-fuel combustion very briefly. So as I said, the goal is to remove the nitrogen upstream, and then we do combustion in oxygen. But it's very hot. I mean, you can probably design some new plants that can accommodate higher temperature, but if you want to retrofit, you want to control significantly the temperature. And this is why we usually recycle, the idea is to recycle part of the flue gas. And then the flue gas is composed mostly of CO2 and water. So here is a brief, a simple schematic of an oxy-fuel system. So you got a boiler in the middle. You need the air separation unit, which you have on the left. Then you can see there's a flue gas recycle, which could be, at least in a power plant, up to 2/3 being recycled. But the good thing is that the stream that goes to the CO2 capture is much smaller. Yeah. And we still need to further purify a little bit the stream here. So in this oxy-fuel, the main energy consumer is the air separation unit. And just to give you an idea of the magnitude, oh, by the way, for the size we are talking about, probably at this moment, only cryogenic distillation would be available. Also, there are other techniques to bring oxygen, but I believe, because it's a huge size, this is the biggest, among the biggest air separation units you would build. So, for example, for 95% oxygen purity, you will require about 200 to 240 kilowatt-hour per ton of oxygen. And if you want to bring it to 99%, but it's even much higher, it's higher. So for a 400 megawatt coal plant, for example, we need 300 tons per hour of oxygen, which represent about 72 megawatts. So you can see the magnitude, like 70 megawatt for a 400 megawatt plant. So this is where you pay the penalty. Okay, so I'm going to skip. This is basically the process to further purify and compress the CO2. Now, something I would like to mention briefly is chemical looping. It's another, that didn't seem to appear in the slide I showed you earlier. It's a technology that has a promise to lower significantly the cost of CO2 capture. And I mean, this has been researched for a long time. And its main advantage is the prevention of CO2 dilution with other flue gas, like the nitrogen. That's what we try to do all the time. And this, basically, we need a metal oxide used as an oxygen carrier. We transfer oxygen from the fossil fuel without mixing with nitrogen and CO2. So maybe it will be clearer if you see a simplified schematic. So we've got so here you will have two reactors. Typically, they would be fluidized bed, where you have solid being transferred from one to another one. And so you've got the metal oxides that react with the air to oxidize the metal. And then this oxidized metal goes to the fuel reactor, where it's reduced by contacting with the carbon and the hydrogen in the fuel. And then you bring this reduced metal oxide back to the air reactor. So a key component here will be the metal oxide. But it has a potential to reduce, apparently, quite a bit the cost of CO2 capture. Okay, so here. So now I want to talk a little bit more of the cost, because this is always something that comes. So here there is something called the Sherwood plot that has been applied for several aspects in chemical engineering. Here it's applied to basically the cost, the capital cost of a capture plant based on the concentration of CO2, where you have a log-log plot. And what is nice is it follows a straight line. It's a linear function as a function of the concentration. So this basically concentration matters. So for example, for NOx and SOx, it will be in the ppm range. Like the CO2 PCC is typically 12%, like from a coal power plant. And the IGCC, CO2 IGCC, it will be 36%. This will be for coal gasification, like the pre-combustion I mentioned before, at 36%. So if there is the take-home message from this slide, if you can increase the concentration of CO2 in your stream by maybe changing whatever you do in your operation, that should help in reducing the cost, the capital cost at least. For the next slide is to give you some concentration range of CO2 depending on the processes. So for natural gas, let's say on NGCC, it's very low, 3 to 5%. Coal, it's a little higher. And then in a refinery, between 3 and 20%. Now, if I look in cement production, it could be between 14 and 33%. So it's getting higher. And in the iron and steel productions, 20 to 27% from the blast furnace. And and it can go up to 42% in the basic oxygen furnace. So we would expect, depending on what you do, if you change your operation to maximize the CO2, it may help reducing possibly the cost. Here are some costs from a relatively recent report, from an IEA report about different technologies. So you can see I'm not going to talk on the very top one. This one is a special one, is the direct air capture. But from the second one, you've got power generation. So the light blue are the one considered with low concentration of CO2, and the darker blue are the one with a higher concentration of CO2. And you can see the trend. Higher CO2, lower the cost. More important for us probably is for the cement and the iron steel, and you can see also the range varies a lot. So it depends on the study, depends on the process, it depends on a lot of things. So for example, on this paper, the cement goes from about 60-ish to almost to about 120. And iron steel, it's a little bit lower. And for the power generations, a little below 50 to about 80. But the carbon capture costs decrease over time, and we don't have too many examples of this. At least in the power generation, we can look at the case of the Bondari Dam, where it was $110 per ton. In that Petranova, where I show you the picture, that's what is claimed. So it's $65 per ton. By the way, that Petranova plant has been stopped. The capture plant last year. Apparently more because of the price of oil than anything else. And is expected to go even further down. And those would be, those would be amine kind post-combustion capture. So here, it's a very busy slide on a very busy report, but I think it's mostly to highlight this report. The IEA Greenhouse Gas has issued a report just a few years ago, not too long, 2018, especially for the cement and iron and steel industry. So if you haven't looked at it yet, you want to look at it. So it's basically a very comprehensive literature survey on CO2 capture in the cement and iron and steel industry, where they try to, because the difficulty is everybody has his different assumption and it's difficult to compare. So they try here to have a methodology to basically to be able to compare all those different studies and came up with some ranges. So now I'm not going to go in the detail which one looks like the better, or we can talk later maybe today. But if I want to point out something is you have two different kinds of CO2 cost here. And this is where things can sometimes get confused. You have the cost of CO2 capture and the cost of CO2 avoided, and they can be quite different. So it's important to understand the difference between these two kinds of costs and maybe when you can apply one or the other one. So this is maybe pretty much my last slide. If you have a plant, so the CO2 capture, the cost of CO2 capture, you can look at the gross CO2, the cost to capture the CO2. The gross CO2 removed, and the CO2 avoided is more like the net CO2 not emitted to the atmosphere. So you could imagine, you could put possibly a capture plant where you capture maybe lots of CO2, but at the same time, you may generate lots of CO2. So that's basically, once you want to take this into account, this is where the cost of CO2 avoided comes into place. So I would say that if you want to compare options, then you should look at the cost of CO2 avoided. It will be a better metric to do comparison. And of course, when you do probably your own economic analysis, then the cost of CO2 capture may be more relevant at that time. So both costs are relevant, but you have to understand what they represent. And finally, if you are interested, there is this nice website that gives you basically a map of all the CO2 capture projects. Those that are demonstrations, those are more industrial applications. So CO2re.co. So this is an interesting website to look at. So conclusion, so if you look at this, you don't have that many commercial CO2 projects worldwide, but it's growing, and hopefully we will see something possibly in Ontario. Okay, so this will conclude. Hopefully you learn a little bit something about CO2 capture. Is that the first time you heard about it? I think I'm past my time. No. Okay.
Well, I thought we geological engineers were expensive, but thank you, Eric. Our next speakers are Robin Hughes and Dave Ryan, who are group leaders at CanMet's Bell's Corners labs outside Ottawa. They're going to discuss the National CCUS Assessment Framework and the work that is going on within NRCan to further capture, transmission, and storage of CO2. And they're speaking to us from Bell's Corners. Robin, Dave, are you with us?
Yeah, just had to unmute myself. Hi. So I think this is a really exciting activity that we're involved in at the lab right now. And it's essentially what we're doing is developing a suite of tools that Canadians across the country can use to evaluate CCUS and essentially develop the engineering economic analysis we need to minimize the cost of CCUS and develop the hubs and all the great things that everybody's been talking about. But we're building it up from the bottom up, and we're going to be including the engineering and economic aspects. But first, I'm just going to have a quick intro to my own group. There's 20 researchers on my team, essentially dedicated full-time to developing carbon capture technology. And we've been doing this for over 20 years now. And we've essentially spanned the entire suite of carbon capture technologies that Eric mentioned earlier. But that's only one of the teams within the Clean Fossil Fuels group. Dave's group's also one of those teams, and there's 3 other teams as well that are dedicated to carbon capture technology development. And all in all, there's 70 researchers at this particular lab that are working on CCUS. Okay, next slide, please. So this really got started when there's the ambition became public that we really want to reach net zero emissions, and it became clear at that point in time that we had to address all of the emitters across the entire country. And the analyses that had been done in the past really had to focus on coal power and oil sands, and so there wasn't really the groundwork had been laid to actually understand how we would do this for the entire country. So that's what we've set out to do. This particular map shows all of Canada and all of the major emitters. So these are emitters of over 10,000 tons per year. And you can see they're separated by sector. So there's oil and gas in pink, there's heavy industry in blue, and that blue is obviously a big focus for Ontario. But also one color you may not have seen on here is the green items. And those are biogenic CO2 emissions. So those are the large emitters of CO2 that's been generated by biomass combustion. So for example, at pulp and paper mills. And that is in addition to the fossil fuels that are actually produced at pulp or paper mills. So I think that really plays into how we're actually going to achieve net zero emissions, because we can't get all the CO2 from all these facilities. We're looking at maybe 95, 98% at best. And the balance of that's going to have to be made up through methods such as bioenergy CCS or that super expensive direct air capture that Eric showed. So we've got this program has started up now, and it spans the entire CCUS chain: carbon capture, utilization, transportation, and storage. And all the required researchers are working on it within the Natural Resources Canada. But we've also got collaborations are set up now from coast to coast, all the way from Victoria and Vancouver, and out to Memorial and Dalhousie, and lots in between. Next slide, please. So what we intend to do is actually produce open source tools, data, and analyses that people can use. So this will be set up in a web sharing websites where we can actually get people to can download the tools, they can do the analysis themselves, or we can work with them to do the analysis. And these are the different types of things that are going to be included in the objectives. So we want to be able to analyze CCS clusters right from the facility level to local regions. So maybe we're looking at something around the Sarnia area, to larger regions, so Southwest Ontario, up to the national level, where we're looking at the entire infrastructure for the country, and also international, because we're also tying into similar work that's being done in the US. So we can start having the tie-ins that we need to ensure we have stable and reliable CCUS transportation and storage. We're going to be looking at onshore and offshore CO2 storage, and Dave will be talking about that later on. Everything like mineralization from tailings, so for example, some ultramafic rocks. The transportation infrastructure there's a big gap in Canada right now. There's been very little research or analysis or engineering that's actually been done on this. So this is a big area we're putting a lot of effort into right now. It's going to support a lot of policy decisions. So it's important for us to get the right data and information and logic as well into this to ensure that the policymakers, whether they're federal government or provincial governments, local municipalities, or the decision makers in industry, that they can go and do the right things and actually help coordinate those decisions amongst those parties. We're using some really new techniques for doing cost characterization. I'll mention that in a bit. And the idea here is, there's going to be a lot of scenario planning, and we're going to have to understand the pathways that we need to go through to actually enable CCUS hubs. And so this is not only a single snapshot of what CCUS hubs and transportation would look like and capture. This is actually going to be multi-year forecasting. We can look out to, say, 2060 and start adding in CO2 sources and transportation networks and CO2 sources as they start up and shut down. And the other thing this is going to do is we're going to be adding in new production of CO2. So for example, if we have blue hydrogen production start up, we're going to be including those in the scenarios. Next slide, please. So one of the first things we did with this is identify where are the clusters of CO2 emitters in Canada. And that's what this map shows. This particular map is showing only clusters of emitters that are greater than 0.5 megatons per year over a 20-kilometer radius. So you can see right away that this is actually well distributed across the country. Right from BC, where it's predominantly biogenic CO2 emissions, into Alberta with their oil and gas and coal, Saskatchewan. There's not a whole lot in Manitoba. Those are largely related to mining. Ontario's got a large proportion of process emitters, but it's also got a lot of biogenic emissions, which is similar to Quebec. And then once we get into Atlantic Canada, a lot of those big emitters are actually related to coal power. Next slide, please. So Eric started to mention the different types of CO2 capture technology, and obviously there's a broad suite, and there's an awful lot more than what he mentioned. But what we're doing is we're commit our 25 years of experience in CCUS technology development to developing cost and performance models for each one of those different types of technologies. And the idea is that we actually have those applicable to the entire scale, right from small emitter up to big emitter, and with the different temperatures and pressures and flow rates and compositions. So all of Canada's 1,600 plus emitters, we can actually get a decent cost analysis, not just the kind of range values that we're seeing from IEA reports, but we can say, my local situation is this, I've got the cost of power of this, natural gas's cost is this, and my labor force is that cost. What does my CO2 capture cost end up being for these different technologies? And that will help us select what is the best technology for any given facility. And that's not just for, some large CO2 stream coming out of a facility, but it's going to be stack by stack or process stream by process stream. So this image I've got here is one of the pilot plants that we have at CanMed Energy. Originally, this was built in collaboration with the Department of Energy, the Gas Technology Institute, Lindy, and the Government of Alberta as a pressurized oxycombustor. Eric mentioned the oxycombustion process. And what we're doing now is we're converting that into that chemical looping technology that Eric also mentioned. And we're doing that with Hatch. And they've got a new type of reactor that we're actually going to apply to that to substantially bring down the cost for chemical looping, even beyond what others have discussed. Next slide, please. So as I mentioned, a big part of this is the transportation planning. It's going to be national scale, but it's also going to zoom right down into the local scale. So this morning, I'm only going to talk about the national kind of scales. This afternoon, I'll be going through some of the analysis we've started doing for Ontario specifically, and we can go through pipelines. This image on the left, we've got clusters of CO2 emitters, and we're looking from about Chicago eastwards towards Newfoundland and Labrador. And the gold and the orange hex bins that we're looking at there, those are all more than 1 million tons per year. And then as you get down into the purples, we're down 500,000 or 400,000 up to 1 million tons per year. So those are all large clusters. And the really convenient thing about all this is you can see it's all lined up nicely. So you can run a pipeline through all that and actually start connecting those CO2 emitters to the CO2 storage sites that extend beyond where I've actually shown the pipeline. So into the Michigan Basin and also to the offshore of Nova Scotia, Newfoundland, Labrador. And we're creating cost optimization algorithms. The first one was actually validated yesterday, so we can now actually go and cost out these pipelines in combination with understanding the cost of capture of the various emitters and the storage as well. And we don't have all this built in yet, but the idea is we're also going to account for potential impact on First Nations lands, protected areas. It will have preferential routing through existing rights of way. We'll be looking at socioeconomic implications and integration of the U.S. potential CCUS networks, which are far more complicated and vast than our own. So it's tying into the U.S. will actually give us a nice safety net so that if we have issues with our local storage at some point in time, we can then go and make good use of CO2 storage opportunities in the United States. Next slide, please. So this is kind of a different a shot of that same arrangement of emitters and transportation modes, our pipelines. But in this particular case, what I'm trying to show is that we're not just looking at pipelines, because pipelines is not going to work for all of the emitters. It's certainly the way to go if you have very large emitters, so say 3 or 4 million tons per year. But we've also got a lot of facilities that it's just not practical to get a pipeline to them, whether it's because of scale or because of their location. So we're also going to be looking at ship-based transport. Like that's going to be important on both the east and west coasts, because a lot of the emitters, it's just going to be very difficult to actually get pipelines to them. And we're also looking at rail service, because there's a lot of smaller emitters out there that we also have to take care of. And you can put about 100 tons of CO2 per rail car. And so it's actually sensible to do this for some substantial scale of equipment. Next slide, please. So what we're trying to do this year is we're going to identify all the clusters and try to get them characterized so that we understand, what types of flue gas they're going to be emitting on a facility by facility basis in general terms. And we'll advance that into more specific terms through discussions with the various emitters. We're going to have all the CO2 storage reservoir data aggregated. You can see an example of that on the right-hand side there. And we're going to have cost predictions for at least 3 CO2 capture technologies. So right now we're talking to companies that actually design and build amine type systems, like Eric mentioned. There's CO2 solutions, and there's a membrane and cryogenic separation process that we're going to be doing first. We want to have some first passes at the CO2 transportation corridors, and with the model actually validated yesterday, we're in a position now where we can probably get first pass on what the actual CO2 transportation corridors will be by about Christmas. And we'll be able to provide interactive graphics that people can actually use to understand how these systems all fit together. So, for example, this image on the right-hand side is an interactive HTML map that includes all of the data that I've been talking about. People can make use of that. And I'm also hoping that we'll have some of this open source code available for release to the public in the coming year. So that's the start. That's an overview of the CCUS assessment framework at the national level. I'm going to talk a bit more about Ontario specifically this afternoon, but now Dave is going to give an overview of our activities related to this for CO2 storage. Next slide, please.
Thanks, Robin. Assuming everybody can hear me. So first of all, I'd like to thank the organizers, so Dick Jackson and University of Waterloo, for putting this workshop together. I think it's well overdue. So back in the early 2000s, late 1990s, early 2000s, CCS there was certainly a lot of momentum and interest across the country, but also Ontario, and it waned for a good decade at least. So it's time to restart the conversation, and this is a great way to do it. So thank you for that. Okay, so changing things, switching the topic a little bit. So my group is focused on the subsurface. So the wellhead down, and the 3 major research areas we have are oil and gas. We focus mostly on the low perm, the challenging reservoirs, shales and low perm reservoirs. CO2 storage, that is in fact how our research group got started back in the late 90s, early 2000s. And in the past couple of years, deep geothermal is, we've added this research area to our portfolio. So we're a group of 7, and again, we focus strictly on the subsurface. I don't have too many slides, 6, 7, which is great. The first one is going to deal with a quick overview of Ontario's emissions, and then a couple slides on CO2 storage estimates. I don't want to delve too deeply into this because I know we have some speakers coming up next to discuss this, and we also have a breakout group this afternoon on that. So I'll just gloss over some of the numbers to really to make a point. Some challenges and opportunities for Ontario, and CCS roadmap that I want to introduce to you. Next slide. Ontario emissions. So according to ECCC, and for those of you not familiar with this acronym, Environment Climate Change Canada, this is the They used to be called Environment Canada, and the first Liberal term that was changed to ECCC. And they are the emissions regulator, the Canadian emissions regulator, for atmospheric emissions regulator. So according to that data, Ontario has about 160 megatons in 2017. The lion's share of that is made up by the transportation sector, large final emitters, and buildings. And of that, about 40 megatons is large final emitters. And the reason why I point that out is this really is the low-hanging fruit. If you want to do CCS on a big scale, then due to economies of scale, you have to start with large final emitters. There used to be a rule of thumb in CCS that anything less than 100 kilotons you didn't pursue. You couldn't make an economic case for it. So, and if you glance down to another point I'd like to make is if you look down to the right, you see a stack chart. Ontario over the past decade, emissions have in fact dropped. So that's the good news. But that is mostly made up from the electricity sector. I don't know the exact reasons why, but I suspect that has to do with fuel switching, moving from coal to natural gas, but also incorporating renewables into the grid. Next slide. I want to mention the North American Carbon Storage Atlas, and there are a couple reasons why I want to do that. So Natural Resources Canada, the Mexican government, and the US Department of Energy in mid-2000s, 2010-ish, carried out a study. It took 2-3 years to get done, and the goal was to produce the CO2 storage atlas for North America. Participation for provinces, most of the provinces did participate, and I'll point out Terry Carter and Andrew Habib from the Ministry of Natural Resources. So they provided data and information, and that went into development of the Ontario component and ultimately the Canadian portion of the NACSA. And really the point I want to make here, and you've heard this, and I kind of figured the numbers, the storage estimates for Ontario and the lifespan of it would be, and there'd be some debate on this, and I was certain that there would be seeing different numbers. So if you look down to the far left column, you see the provinces. So the provinces in Canada, and Ontario is pointed out. And the next column shows the emissions for Ontario. And I should note that this is 2009 data. So funny thing is, it hasn't changed much. According to 2017 data, it's 40 megatons. So no big change there. And if you look to the far right, this is where we get the storage capacities, but also the concept of storage duration, which is the lifespan. So if you were to capture and inject those 40 megatons per year continuously, how long are you good for? And according to this study and the numbers that were run, it's about 30 years. Now, you've heard earlier today from speakers that 10 years, we've heard 10 to 15 years of lifespan. Well, is it 30 years? Sensitivity analysis run also during this study said, well, it could be 3 times as much as that. So, so the non-geological folks in the crowd are probably thinking like these guys know what they're talking about. Is it 10 years or is it 90 years? We don't know. And that's one of the points that I want to make here. And I'll come to a recommendation. I think it might be in the next slide. But the other point I want to make here, which I think is going to be important for Ontario, is cross-jurisdictional cooperation. If it's 10 years, if it's 30 years for Ontario of storage capacity, longer term, we're going to need to cooperate, and if we're serious about CCS, we're going to need to cooperate with other jurisdictions. And I'll come to that shortly. Next slide. I'll gloss this over. So this is the storage capacity, some of the earlier work done in the 2000s from the Ontario government, and also a CanMet colleague of ours, Ahmed Shafin, looked at the Mount Simon the saline formation in Southern Ontario. The only point I want to make here is that we have not exhaustively studied storage potential for Ontario. Oil and gas pools included. They were they're usually ruled out because of they're relatively shallow compared to other oil and gas producing regions of Canada. And somewhere around 800 meters deep, CO2 becomes supercritical. So a reservoir above that a cutoff was applied and was almost eliminated from storage potential because you just couldn't get the density and you couldn't maximize CO2 storage in these shallow reservoirs. So some studies were done, but not exhaustive. The Mount Simon Formation was looked at. It was seen as the best prospect for saline formation, for saline storage in Ontario. 730 megatons was the number that was generated. So the challenge is we've got 40 megatons of CO2 to deal with, and according to the numbers, limited storage capacity. So the challenge is pretty big if we want to reach net zero by 2050. Next slide, please. So this is where we get into, well, the opportunities. Some would say these are challenges, but I would start off with just reevaluating Ontario's storage capacity, particularly the saline ones. I wouldn't limit it to that. I would definitely look at the oil and gas pools. But so why is because when some big assumptions were made when we came up with those the storage capacity estimates, sweep efficiencies, porosities, they were assumed, and we really didn't do any petrophysical studies to back up those estimates. The other we can do is look at some of the poorly understood reservoirs, so the shales and the low permeability reservoirs, such as carbonates, and they were also cut off from the study back in the day. So if you remember the shale gas boom, where these formations held a lot of methane and hydrocarbon gases and liquids, but they couldn't extract them. Well, the technology has changed, and can we get CO2 into these shales and these low perm reservoirs? I think we need to take a look at those as well. So that's a domestic easy starts that we can do, in my opinion. I say easy, but there's a whole lot more to it than that. And then moving out of jurisdiction. So transport the CO2 outward, and Robin touched on that, and we'll say more about it this afternoon. But so if you look at the map to the right, you see the pink, the top one with some of the pink. So that's a sedimentary basin, and the point here is that it's shared with the United States. So if we want to think long-term CCUS, then I would recommend opening talks with. We should talk coordination with some of these states, in particular Michigan, Pennsylvania, Ohio, and New York. They have big capacities, much bigger than Ontario. It's connected. That's the good news. And if you look at the small map to the bottom right, it deepens. So it's down dip as you move southwest and southeast of Michigan and Appalachian basins. Other options are moving the CO2 to the Atlantic, so that could be offshore into oil and gas formations. An example would be the Sable Island gas formations, which is depleting, and or to a CO2 terminal for shipping the CO2 to hubs in the North Sea, such as Norway. Another alternative is moving the CO2 west, the Western Canadian Sedimentary Basin. Next slide. Honorable mentions for the hydrogen economy. I was reluctant to have a slide in on hydrogen, but I think it's worthwhile bringing into the discussion, even though I think the focus is on CO2 storage, or CCS, for Ontario. And there's a reason for that, is with recent interest, whether it's blue or green hydrogen that you're doing, you're going to have a gas, whether it's CO2 or hydrogen, and you're going to have a lot of it. If it's hydrogen, you're going to need a lot of it if you're thinking of converting an economy to hydrogen as a fuel. And you're also going to have a lot of CO2 to deal with. For blue hydrogen, you pull out the carbon from a hydrocarbon, say a methane, and you've got a CO2 molecule to deal with, and you're going to have to store it. So storage capacity is going to be required. Buffer capacity is going to be needed for hydrogen. So the time to look at these together, I think, is coming. Now, because of the quantities of hydrogen that we're going to need, surface storage is certainly possible, but because of the quantities that we're going to need, subsurface, so underground hydrogen storage. But there are some big challenges with this, and that's really what I need to point out here, is it's in its infancy, and a lot of work needs to be done before we start doing that. So which reservoirs can we inject CO2 and store CO2 into? Well, and Maurice Dussault in the audience can easily speak to this subject. He's done some work on this, but salt caverns represent the early opportunity. But beyond that, clay rocks and oil and gas reservoirs, we don't know. And there are some reasons for that. Leakage, so cap rock and wellbore integrity is going to be an issue. Transport mechanism, so how is that hydrogen going to react in the subsurface? If you're producing hydrogen and you're injecting into the subsurface, and that's your fuel source, ultimately you want to be able to reproduce that. Well, is that hydrogen going to become residually trapped in the spore space? Is it going to become adsorbed and locked there, so you no longer have access to it? These are very basic questions that have not been answered. And we know it's going to be reactive. Hydrogen is a pretty reactive molecule. So redox reactions, biotic, abiotic, they may be significant. And I do have some colleagues on the line with another directive of ours, but their standards are being developed for hydrogen. But I'm not sure about subsurface, and is there a need for that? We have CSA Z741 for CO2 storage in Canada. Maybe hydrogen storage standard will be needed, and I would expect that will come if hydrogen as a fuel source for Ontario takes off. Next slide. Changing the topic to CCS, or introducing the CCS roadmap for Ontario. So we've heard a lot of moving parts, and I think, if anything, Ontario has the biggest challenge. The Western Canadian Sedimentary Basin, the province of there, are blessed with great geology. They have plenty of pore space, and it's all over. Ontario, not quite such the case. So it's more complex. So after some discussion with some external colleagues and internal colleagues, we decided that this is complicated for Ontario. So we decided to take rather than jump into it and do research, just start doing research, let's take a step back and evaluate things. And so we pitched the idea of a CCUS roadmap. So, and we're expecting this to get started this year and run into 2022. And the objective is to identify a path forward for CCUS in Southern Ontario, and to develop options that will meet the GHG reduction goals for Ontario. Who should be involved, or who is the audience? And it's industry, governments, and academia. Roadmaps, this is not a novel concept. A few of them have been done in the past, and they're typically industry-led. So why industry-led is because we want to hear, so ultimately the technology is going to be adopted by industry, and we need to hear from industry what they see as the challenges. And so that's the purpose of this, is to be driven by industry. Tell us what you need to be able to do CCUS. So government, of course, is at the table somewhere in the picture, but we want to hear what you have to say. That's the key message here. And the purpose is to provide to develop a long-term vision and to identify the key technical issues. It doesn't have to be technical, but normally that is the focus of a technology roadmap that will and address those that will, so we see deployment of the technology. I'll just mention a couple of them that have been done in the past. So these are the technology roadmap to improve wellbore integrity, which finished up in 2018, and that was led by CanMet, by a colleague of mine, Andrew Wigston, and an earlier one on a CCS roadmap in 2006. These are the days when CCS was a bit of a novel concept still. So I don't expect an exhaustive exercise like that roadmap, but something more focused on Ontario's needs. And I think this might be the last slide. So thank you for listening, everybody.
Thank you, Dave and Robin. We'll go on now and hear from the Ontario Petroleum Institute and the Oil, Gas and Salt Resources Library in London. Although some politicians 15 years ago didn't know that we had an oil patch in Ontario, it's a historic oil industry, oil and gas industry, and it is still alive and kicking. And there's an enormous amount of expertise within the Ontario Petroleum Institute, represented by companies engineers, geoscientists, and service industries. And we wanted to hear from them, and it will be useful for everybody to understand how to get in touch with them. Our speaker will be Jim McIntosh, who's the chair of the board of directors of the Ontario Petroleum Institute, and Jordan Clark from the Oil, Gas and Salt Library in London.
Are to promote the interests of those engaged in the upstream oil and gas industry, to promote study, research, and communication in matters relevant to the industry, to keep our membership informed on developments affecting them as the industry, to cooperate with government and the public in developing and modifying regulations that regulate the industry, to encourage environmental and sustainable development of the sedimentary section within Ontario, and to hold an annual conference to discuss relevant technologies and to promote collaboration within the industry. The OPI currently consists of 20 producing companies, 2 utilities, 17 consultants, 5 legal or 27 oil field service companies, 2 drilling contractors, 3 educational agencies, 1 cavern storage operator, and 18 government ministries or trade associations. OPI members understand the reservoir characteristics and problems with all producing oil and gas reservoirs in Ontario. OPI member drilling and cementing companies and consultants have direct knowledge of potential drilling cementing problems and formation characteristics of most aquifers in a sedimentary section. OPI producers and engineering consultants have designed, constructed, and are operating oil and gas production facilities, so we know how to build pipelines and install facilities in Ontario. And OPI has a long history dealing with the provincial government, especially the Ministry of Natural Resources and Forestry within Ontario. How can OPI help develop carbon sequestration? We understand the reservoir characteristics of potential carbon sequestration containers, so contact an OPI member or the Oil, Gas, Salt Resources Library. The library has proceedings from over 50 years of OPI conferences, plus has the last 3 OPI conferences on video. The OPI can help lobby the Ontario government for changes to the Oil, Gas and Salt Resources Act and regulations that will be required to allow carbon sequestration to go forward in the province. And it will ensure that the changes are safe, reasonable, responsible, and workable. Please contact OPI at the link below. Thank you very much for your time.
Hello, my name is Jordan Clark. I'm the manager of the Oil, Gas and Salt Resources Library, a facility dedicated to enabling Paleozoic bedrock exploration in Ontario. We archive data and rock samples for thousands of locations across Ontario that you can access to start exploring and building your projects today. The Oil, Gas and Salt Resources Library manages data and organizes research on boreholes drilled in Ontario licensed under the Oil, Gas and Salt Resources Act. This includes oil and natural gas wells, but many other types of boreholes as well, such as salt solution mining wells, injection wells, disposal wells, deep stratigraphic tests, and storage wells for natural gas, liquefied petroleum products, and compressed air energy. The library receives rock chip samples, rock core, geophysical logs, geological and engineering data from these borings drilled in Ontario. This material is processed at the library and made available for viewing. These materials can be viewed at the facility as well as online. Information from nearly 27,000 borings, all drilled in Ontario's Paleozoic bedrock, can be accessed in the library catalog. The well files are available in a standardized text format and as a complete scan of the original file. Data from these wells includes geological formation top picks, fluid zones, production records, porosity and permeability data, engineering data, and plugging records. Some of this data may be enhanced by the library and provided to our members as a database, such as 500,000 monthly fluid production reports and 50,000 porosity and permeability measurements taken from 500 borings. We archive many rock samples from across Ontario. Nearly 11,000 wells have a set of cuttings at the library. Cuttings are rock chips collected at 3-meter intervals during drilling. These cuttings are available for viewing and testing in the library. Over 200 sample trays and thousands of microscope photos from 100 key wells are available for viewing online for desktop researchers. 1,200 cores from over 1,000 borings are also available for study. A complete set of photos, including dry, wet, and ultraviolet fluorescence, are available for over 300 wells to help refine your search remotely. Deep formations such as the Cambrian have the fewest wells, about 900 in the Cambrian. Still, geological data, chip samples, geophysical logs, and rock cores are available for study and characterization of these deep bedrocks. Over 80 rock cores in different locations are available to help you study the Cambrian, and that many plus half are available for the slightly shallower rocks of the Ordovician Carbonate. Staff at the library are available to help you find the right data for your project. We are constantly improving and making more data available with the support of our members and project partners. For example, the library is using its data to help create a 3D lithostratigraphic model for all of Southern Ontario that is available as a free release from the Geological Survey of Canada and Ontario Geological Survey, with further updates and refinements to this model just being released. To immerse subsurface explorers in the model even more, virtual reality experiences and 3D prints of the model were created and can be created for any area. If you are considering starting a research project into the Cambrian or any other Paleozoic bedrock layer in Ontario, the data and physical rocks held at the library can help you get started nearly instantly at very low cost. Some things you can do right after this workshop ends to start exploring Southern Ontario's Cambrian geology, and these links will be on our Twitter at twitter.com/OGSRlibrary. Number 1, download the 3D lithostratigraphic model of Southern Ontario. 2, watch past conference talks highlighting resources of the subsurface and our virtual reality tour of the model. Headset is not required, but is a fun experience for those who have one. 3, sign up for a free website trial and explore our database. Go to ogsrlibrary.com/free and use the code EXPLORE, or sign up to our monthly industry drilling activity newsletter with a code for a longer trial period. www.ogsrlibrary.com/newsletter. 4, download Google Earth overlays from OGSR Library and from the OGS Earth website. 5, visit the library in person to view cores and cuttings from relevant borings. Thank you for your time, and please enjoy the remainder of the workshop.
Thank you, Jordan and Jim. We want to proceed now and start the first of 3 discussions we're going to have on geological sequestration of natural gas. The speaker is Steve Party, who is manager of the natural gas storage group within Enbridge, based in Chatham. And Steve is going to brief us on the storage operations within Southwestern Ontario.
So again, as Dick mentioned, I'm Steve Party. I manage the underground storage group for Enbridge based in Ontario. I've been with the company about 28 years now, and pretty much all of that has been either in underground storage or in business development or operations related to underground storage. So I've certainly had the opportunity to be involved in the development of the underground storage system and I started with the company kind of in our storage planning area. I got to do some of the reservoir engineering, some of the well drilling, managed the technical aspects of the group, and so there's certainly been a lot of opportunity there, and certainly seen the system grow over all those years too, which is important. So Hilary had showed this map a little earlier, and just gives kind of an overview of the underground storage system and where it's located. You can see within Southwestern Ontario and all the interconnecting pipelines that go throughout the US and the position of Dawn and the storage system. So we talk a lot about these days about energy storage, and I would say Ontario as a province has kind of a crown jewel when it comes to energy storage, and we've been doing that for 75, actually coming up on 80 years, I think, next year. So there's certainly been a lot of growth through that system. The Dawn Storage Hub kind of starts in just south of Sarnia there, and then the Dawn Parkway system kind of moves gas from Sarnia all the way through to Toronto and connects with other interconnecting pipelines there. A lot of the gas that comes serves the province comes through Dawn, whether it comes in through interconnecting pipelines and then into our storage system in the summer, and then those supplies are supplemented by the storage system that we have. So certainly we have an integrated hub model with respect to the storage. There's 35 storage fields that are connected to Dawn, and those are connected by a series of pipes and compression, and then all of that's interconnected in our Dawn facility. Within the Dawn facility itself, there's in excess of 250,000 horsepower of compression to help move the gas that comes in on the supply pipelines and also at a storage. And just to give you an impact that the storage system has on the province, you look, thinking back, one of our peak withdrawal days was there was about 6.5 PJs of gas that came out of the system, or petajoules of gas that came out of the system, and it was in January of 2019. There was an upset event in Michigan on that day, and about 6.5 PJs of gas came out of the storage system. All of the gas coming out of Dawn, there was only about 7 PJs. So in excess of 90% of all the gas that was serving the Dawn Parkway system and subsequently serving the province was coming directly out of the storage system. And that obviously has a big impact on our energy stability and our energy reliability within the province. So as I mentioned, over the years, we've kind of started in and around Dawn was the first 2 storage fields that we had about 75, 80 years ago. And then the system has expanded from there. And we've certainly got the benefit of geology. So all of those reservoirs, or especially in the ones in around Lambton County, they're about 500 to 600 meters deep. They're all Silurian age pinnacle reefs that we're storing gas in. And the pressures in those reservoirs range from about 8,000 kPa up to about 11,000 kPa. There's about 350 injection withdrawal wells that serve all those reservoirs. Each reservoir kind of operates independently and is connected back to Dawn, and through a series of pipes and compression, as I mentioned. And then within each reservoir, there's certainly a variety of sizes of reservoirs. The characteristics of those reservoirs are certainly important. So I think our smallest reservoir is like 0.3 PJs, and our largest reservoir is 30 PJs. So you certainly see a large range in different sizes also that you see there. All of that storage system enables us to provide a lot of services for the market. That includes not only the customers that are in Ontario, so our in-franchise customers that we serve within the province, but also other customers, marketers in and around the US and Canada that transact gas at Dawn. Dawn is, as Hilary mentioned, the second largest hub in North America. There's a lot of parties and counterparties that transact, buy and sell gas, buy storage services. A lot of the natural gas-fired power plants in the province have storage services at Dawn that provide both standard deliverability and also high deliverability services. So that hub model and is very important to the province. And it's able to interconnect all that storage. And really, from the customer's standpoint, really it's a seamless what's happening in the background. And the fact that there's 35 different storage pools with different characteristics, different sizes, permeabilities, porosities, really when a customer transacts at dawn, they're just buying a certain amount of storage at a certain deliverability, and they can be assured that firm service will be delivered on the days that they need it. So that's kind of important to the growth of the system. As was highlighted by Jim and Jordan, there's certainly a lot of information that we have on the geology within the province that's available to use. And I think it's about extending a lot of the information that we have, a lot of the technology that we have today, and extending it into the CCUS space. So certainly all the knowledge that we have as a company and as an industry of what's the subsurface in Southwestern Ontario. There's certainly a lot of, I know out of our 35 different storage pools, we have 3D seismic sets over all those storage reservoirs that we can use to kind of interpret what's happening. We've done a lot of geomechanical modeling. I see Geofirma over here. We've worked with them to do a lot of geomechanical model as we've tried to expand our storage system. And certainly a lot of existing wells. I was thinking earlier that within the Cambrian, one of the disadvantages is that there's not a lot of wells, but one of the advantages is that there's not a lot of wells also. So that'll certainly help moving forward. And really, I think it's taking all that information that we've gathered and leveraging it to study in different formations, whether it's the Cambrian or looking at some of the deeper oil and gas reservoirs within the province, which each has their advantages and each has their challenges. But really taking that and making sure whether we can reinterpret some of the seismic that we have to focus it on some of those deeper formations, looking for opportunities to shoot new 3D seismic in areas that we're interested in. And certainly as we move forward, it'll be important to have opportunities to drill test wells and pilot wells to really understand more what the CO2 will look like and what those opportunities are to inject it into the subsurface. And then obviously with a natural gas storage system, there's a certain amount of measurement and monitoring that we're doing for the gas that we're injecting into it. And I think that'll be even increasingly more important and as we move into CO2 storage and the opportunities there. This is a map that was shown earlier. So certainly from the Cambrian standpoint, there's some opportunities, but there's certainly a lot of unanswered questions and research. And as I mentioned, seismic and test wells that need to be explored also. So we certainly, as a company, look forward to be playing a big role in that. And we certainly also appreciate, I think earlier last week, or within the last couple of weeks, the Ministry of or the Ontario government made an indication that they certainly want to take some time to clarify some of the carbon sequestration regulations in the province. And we certainly look forward to working with them and industry working with them to kind of put that framework in place from a regulatory standpoint. So I think that's encouraging from a provincial standpoint and encouraging as we move forward. I mean, I think regulations are important. It's been an important piece of kind of the natural gas storage industry as we move forward. And it'll be important as we continue to develop into CO2 storage also. So again, thank you for the opportunity to speak today, and I'll be around. And if others have questions, like I said, I've worked on the storage system for quite a while, so to say it all in 10 minutes is always the challenge, right? So thank you very much.
What was one of the interesting points Steve just brought up is the safe storage of natural gas at pressures up to 11 megapascals, 8 to 11 megapascals, I think Steve mentioned, in shallower horizons, geological horizons, than we're looking at for CO2 sequestration. The bottom line is we can store gas, whether it is natural gas, methane, and so on, or CO2 safely in the subsurface in southwestern Ontario. And that's a tremendously important principle to remember, because there will be suggestions made, I'm quite sure, that safe storage of CO2 may be problematic. Well, I think Enbridge's history over 75 to 80 years shows that that is not necessarily the case. Our next speaker is Maurice Dussault, Professor of Geological Engineering here at the University of Waterloo. Maurice is going to start taking us through the sequestration issue with respect to CO2 and what is required by good geomechanical engineering, geological engineering practice, and what is expected by the Canadian Standards Association guideline on carbon dioxide sequestration. Maurice Dussault.
Thank you, Richard. There, freedom, or liberation from a muffled voice there. I'm just going to review at a fairly high level some of the geomechanics, some of the geotechnical issues associated with CO2 storage, basically posing questions that must be answered. Our options are not huge. There are many pathways of different magnitude, such as reforestation and other pathways like that. But in the subsurface, we're essentially looking at saline aquifers or natural gas depleted fields that had natural gas in them, which will be addressed in the next presentation. So, saline aquifers are essentially the option that we are looking at. Site selection and characterization has to precede facility development, as I mentioned earlier this morning. The major factors are capacity, injectivity, top seal, depth, location, and security. When these are all okay, then we can rank sites. When we rank sites, then we can give certain quality assurances that will guide the development of the capture and transport sectors. The Cambrian has been mentioned several times because it's deep and it has some pore volume available. And the major regions are the northern shore of Lake Erie here, and Natticoke is about centrally located in that ellipse. Along the northwestern shores, Windsor area and the Sarnia area, parts of Lambton County. This is not to say that there are not other sites, but these are the preferred locations in the Cambrian strata because of depth and thickness. The Cambrian strata become thicker to the southwest in the Natticoke, Chatham, Windsor corridor. So those are the sites in the Cambrian. We have to know the initial conditions. There's an old saying, in order to know how to get there, you have to know where you're starting from. So, pressure, temperatures, stresses at depth, plus the rock properties. Pressures and stresses will guide the limits of sequestration. In the Dawn facility, pressures above the hydrostatic pressure, the pressure in the surrounding pore water, are possible in the short term and have been demonstrated to be viable. We are not exactly sure if we can do that in the long-term carbon dioxide sequestration, but we certainly have to make sure that the pressures never, ever get close to the pressure of hydraulic parting. That would open up pathways that we don't want to open up. And temperature effects will be important if we're putting in carbon dioxide at different temperatures. So we have to know these intrinsic site conditions. So for example, in this diagram here, you'll see that the black line, which is the horizontal minimum stress, is larger than the red line, which is the vertical stress, and that is the stress condition here in Ontario. It means that these stresses in the horizontal direction are actually larger than the vertical stress, and this condition exists down to a depth of at least 600-700 meters, and maybe all the way through the sedimentary column down into the igneous rock. But we have to measure them. This is hypothetical, suggested by many data points, but we have to know those stresses in order to design. Capacity is the first of the criteria. Now, bullet number 2 says the theoretical maximum capacity is the porosity times the volume of the rock mass. But you will only access somewhere between 15, 20%, maybe 50% of that volume, depending upon a number of factors. And in the fluid flow business, there are 4 what I call flow instabilities, or displacement instabilities, rather, that will plague us, and we have to understand them, quantify them, and apply them to our target reservoirs. One is gravitational segregation. Carbon dioxide is buoyant, so it will go to the top, making the displacement of the bottom water more difficult. The rocks are comprised of pores and pore throats. Small pore throats will inhibit the displacement process of carbon dioxide displacing the pore water from the capillarity effect. Permeability heterogeneity exists in all geological environments, and that will lead to channeling or preferential flow along the more permeable layers, which will leave less permeable layers isolated and unavailable for carbon dioxide sequestration. And finally, viscous fingering, where if you inject a material of very low viscosity, it tends to finger through the material of higher viscosity, in this case, saline water. So we have to understand these things, and the bottom bullet also is an important point. It basically says, what is the effect of injection on the large-scale pressurization of the subsurface? We must have a better understanding of that. So this is viscous fingering. The blue fingers are low viscosity material that tend to finger through the part of the porous medium that has higher viscosity fluid in it. This is permeability instabilities, or if you wish, permeability heterogeneity, where preferential flow will occur in the zones of higher permeability, abandoning or restricting access to the zones of lower permeability. This is the capillary flow blockage concept, where a different fluid has a surface tension between it and the water that you are trying to displace. And that surface tension inhibits the ability of that fluid to go through small pore throats, therefore isolating more volume that you can't use. We need probabilistic carbon dioxide capacity assessments. Without that, we really can't move forward to capture and transportation. And this has to be done fairly rapidly. We need injectivity. And if vertical wells don't cut it, then we can always use horizontal wells there we go, horizontal wells, which can, of course, be placed in lengths nowadays of up to 3 kilometers, no problem, in a reservoir, giving you a great deal of injectivity. And these will be placed in optimum locations, and that depends upon understanding the geology and the distribution of the porosity and the permeability. For example, if you are displacing brine downwards to the left in a saline aquifer situation, the CO2 is buoyant. It will gravitationally segregate up to the top. And the location of your horizontal well starts to become extremely relevant to achieve the goals that you wish to achieve. Because of the buoyancy of carbon dioxide in the pore space, it has a density of approximately 0.8 grams per cubic centimeter compared to the density of brine, which is 1.2. So as the column of CO2 is higher, the buoyancy pressure is greater. So the importance of a top seal is quite critical. Everybody talks about supercritical conditions. In Ontario, where the rocks are fairly cool, it is actually probable that in some reservoirs we could be just in the range of liquid CO2, just outside of the supercritical range, and that density is still fairly high, 0.7, 0.75 grams per cubic centimeter. Okay? So this is just a phase diagram for CO2, and we must understand the phase behavior of CO2 in order to develop these models of capacity. Site security, and this means security against future leaking. This is an image of a leaking well in southwestern Ontario, and those of you who keep up to the news will remember about 2.5 months ago an explosion in downtown Wheatley, Ontario, from a leaking well that caused the accumulation of methane in a basement, and boom, building destroyed and adjacent building damaged. No one hurt, fortunately. All of our reservoirs have been penetrated by wells. We have to understand the possibility of these as pathways. That's the security issue. Legacy wells are not sealed to the standards of today. These wells may degrade security. We have to solve that problem and maybe turn some of those legacy wells also into monitor wells. So who sets the rules? Well, the regulatory agencies, but we don't have rules yet in Ontario set by the Ministry of Natural Resources and Forestry, and that will happen. And it's very likely that they will follow the guidance of the CSA group that in 2012 published the Z741 standards. And just basically to go through this, I am assuming that the regulators will choose the CSA Z741 standard to guide them in their initial work, along with the Alberta standards, which are more mature than in any other jurisdiction in Canada. So those are going to guide the future. But I want to point out the bottom point. Even though the CSA standards do not discuss the regulator being deeply involved in the site selection and characterization process, I think that we have to work with the regulators sooner rather than later. And they also need our help in this novel task. So I took this graphic from the CSA standards and added my own numbers on it. So I added the timeline that you see in the dark letters there. Site screening and selection, 2022 to 2025, but we have to start characterizing the best sites as soon as possible, starting in early 2024. Development and commissioning of the capture and transportation system has to happen very soon thereafter in order to start injection in 2029. With the limited pore volumes that we have in Ontario, perhaps the cessation of injection will happen in the 2040s sometime. We don't know those numbers yet. You notice on the middle blue arrow, just above the bottom, the regulatory authority box is blank in the CSA report. I'd like to put some exclamation marks there and to suggest to you that it's really important to involve the regulators as early as possible. They must be at the table. (741) also provides guidelines for community engagement, risk evaluation, project management approaches, etc. So at this stage, we are concerned with Chapter 4 of Z 741. That's the chapter that outlines what you have to do or should do for good practice in site characterization and selection. Please, all of you, read that chapter. It's a good, high-level set of guidelines. And then finally, there's performance monitoring in the subsurface, monitoring wells, continuous surface monitoring with ground deformations, for example, or microseismic monitoring. These will be required by the regulator. Episodic 3D seismic surveys, perhaps, and of course, we're going to keep track of the amounts and the temperatures and the pressures and the compositions as a function of time as we do a project. These are the main issues in the geomechanical domain. Thank you. Yes. Good idea. And my mask.
Now we're going to go a little bit deeper into the issue of what is a potential sequestration reservoir for carbon dioxide. But as Dave Ryan said, there are more questions than there are answers. But I will start this discussion, and this afternoon Robert Walsh of Geofirma will continue it following our question and answer period that we're going to have starting at about 1 o'clock. And Maurice, Eric, and Royden are going to moderate questions from you, the audience, whether here in Waterloo or out there in the ether, and answer some of the questions that we know you have, or at least try to answer some of the questions we know you have. My colleagues are Bruce Hart, who's now back at Western after a long swing through Quebec and through the U.S. Maurice graduated from Western with a PhD in petroleum geology, taught at McGill, taught at Penn State, taught at New Mexico Institute of Mines, and then switched to the oil industry, worked for ConocoPhillips and Equinor, the Norwegian oil company, and last winter came back to Canada from Austin, Texas. Scott Mundell, this is I'm sorry, this photo is a bit old. I apologize to Scott. He sent us a new one and somehow didn't get him included. Scott is in the Department of Chemistry at the University of Windsor and has done a lot of work out west on carbon sequestration projects, particularly in the monitoring, in the measurement, monitoring, and verification end of it. He's in the Department of Chemistry at the University of Windsor. Okay, to get to the nub of the problem, our biggest challenge is to match sequestration sites to CO2 sources. A quote from Sally Benson and David Cole, who both we used to be with the national labs in the U.S., Sally Benson is now a professor of engineering at Stanford. That's the nub of our problem. Again, here's our picture of industrial southwestern Ontario. You'll notice that I've divided it up into several zones of emission. There is on the west, there is Chemical Valley, Sarnia, Lambton County. In the center, there are the cement and lime and auto industry plants around Woodstock, St. Mary's. Further southeast are the Stelco plant and the Imperial Oil Refinery down in Nanticoke. And to the northeast is the steel industry in Hamilton. This doesn't show all the industrial emitters, and there are some significant ones like Algoma Steel up in the Sioux, and pulp and paper plants, and some in Lake adjacent to Lake Superior, and the cement plants along the Lake Ontario North Shore. And of course, within Greater Toronto Area, there are several significant producers. Total Southwestern Ontario production, according to the Environment Canada, Climate Change Canada estimate of 2019, was about 20 million tons for this set of industrial producers. As Dave Ryan says, you've got to pick a number. Well, this number is based on the 2019 Environment and Climate Change Canada estimates that have been made public in the spring of this year. So what sites do we have for CO2 sequestration? Well, we got the saline Cambrian aquifers, particularly the region Haldimand, Norfolk, as Maurice pointed out, and in the area of Lambton County, where Shell and Enbridge have interest in establishing a test site. And then there are depleted oil and gas fields, such as the Inner Kip, which we'll come back to, other Cambrian sandstone oil fields, not very big, and perhaps the Ordovician carbonate oil fields in southwestern Ontario. This is a vertically exaggerated picture of the Michigan Basin in southwestern Ontario. The length scale, the x coordinate, if you like, the abscissa, is 600 meters, roughly 600 meters in length. And it is drawn through the Bruce site across Michigan into Lake Michigan. The vertical scale is only about 6 kilometers. So this is about 101 vertical exaggeration, which we do in the geological sciences to show detail. Otherwise, if you squashed it all up, you wouldn't see the detail. Now, at the bottom is the Precambrian basement that underlies so much of North America. It even pops up in its surfaces even in the hill country of Texas. And just above that is the Cambrian sandstone, and it's showing to be vanishingly thin. Now this is the Bruce site up here. This mountain here, because of the vertical exaggeration, is nothing other than the Niagara Escarpment. So this was boreholes that Geotherma drilled in about 2006 at the Bruce site, looking for a potential nuclear waste repository. Here's Lake Huron, Michigan itself, and you'll notice that formations that are relatively shallow in southwestern Ontario are extremely deep underneath Michigan, even if they're geologically younger than the Cambrian. the Cambrian sandstone is our best bet, at least to begin with. What are we looking for? Well, we're looking for thick zones of permeable rock, continuous over large areas. We have a rule of thumb, a measurement, that gives us some idea of whether or not we're in the right ballpark. And this is the injectivity index, and it's the ratio of the injection rate that you can inject CO2 into the aquifer divided by the pressure difference. If this is an injection well, and right down at the bottom here, we have a well screen. So the gas is injected here, CO2, and it comes out this well screen here into the formation. And this delta P is the difference between the pressure in the formation and the pressure in the bottom of the hole. And you want, in a good permeable receiving formation, sequestration reservoir, you want this, whoops, gotta go back. In a good formation, you want this delta P to be very low to make J big. So bigger is better, bigger is better, small delta P and big Q make this large. That's what we're after. But we are constrained. So we'll be using this injectivity index measured in metric tons per year per kilopascal of head difference. And this is some results from existing sites in the Cambrian sandstone elsewhere in North America. Aquastor, we've talked about, is in southern Saskatchewan, right along the border, storing CO2 from a Saskatchewan power plant. Has a J of about 20 metric tons per year per kilopascal. This, the abscissa here, the x-axis, is the product of permeability times thickness. And we find that there's the multiple of the permeability times the thickness of the permeable section is log linearly related to the injectivity index. Now this is just a very rough guide, but you can see that some of these Cambrian sandstones, like the Illinois Basin Decatur project up here, which is in CO2 from an ethanol plant, they got good permeability and thickness. This is a Duke Energy plant in Kentucky. Aquastor is down this end here. Not such good permeability thickness. We got to keep in mind these CSA guidelines that Maurice just mentioned. We want greater than 800 meters depth, so we can get up to 9 megapascals in pressure. That will allow us to have the CO2 retained in situ at under supercritical conditions. As Steve Pardee says, they're already doing this in shallower horizons down in the Dawn project, the Dawn set of pools in southwestern Ontario. So this is eminently feasible. We're going to be sealed by a competent cap rock with minimal groundwater inflow from surrounding rock. That is quite critical to make this work. And there are a whole bunch of preferences we have for moving forward. Okay, now Bruce Hart has prepared several figures for us using the work of Bailey and Cochran from the 1980s. when there was quite a bit of interest in the Cambrian in southwestern Ontario because of the discovery of natural gas and oil fields in this area. Now, what you'll note here is these are elevations in meters above sea level, and the numbers are negative. That's minus 800. So this is the contour line of where the Cambrian aquifer, the top of it is at 800 meters below sea level, minus 800. So you got to put on another couple of 100 meters on top of that, because in that area the ground surface is 200 meters above sea level. So this area around here, down here in southern Norfolk County and Haldimand County, they are the Cambrian starts at over a kilometer depth, over 1,000 meter depth. That's the 800 plus 200 meters above ground surface. So those are attractive areas. You can see down here we also have attractive areas as far as depth goes. Unfortunately, when you look at the thickness of the Cambrian in those areas, it's best along the north part of the Lake Erie shore here and around Windsor. Now, Windsor, there's that area around Windsor is interesting, but it is also, there are quite a lot of developed wells there, oil and gas wells, and salt wells. So there are problems with that. And any injection of fluid into a saline aquifer down there could cause problems across the border. So we would have a boundary waters issue that would have to be resolved. So right now, on the basis of this, we're looking at some of these areas. Like the Shell Enbridge project is interested in being near Chemical Valley. We're also having discussions with the steel sector on this area along the north shore of Lake Erie. Now let's just turn to a depleted gas field. This gas field is in between Kitchener, Stratford, and Woodstock. It was developed mainly in the 1980s and 1990s and has produced a substantial amount of natural gas. It's interesting, of course, because it's within 80 kilometers of Nanticoke and of Hamilton. It's close to these cement plants and lime plants and some of the assembly plants. And of course it has depleted pressure. It's depleted because they've been pumping the natural gas out of it. It seems to have relatively little groundwater inflow. And it's well characterized. That's one thing you get with a depleted oil and gas field. The characterization has already been done by the reservoir engineers and geoscientists who've been using this field to produce oil and gas. And it's also close to the pipelines between Sarnia and Hamilton that are existing already. Well, this is a close-up of the Innikip field and an oil field just south of it. You can see where it is. Here's Highway 401, here's Highway 403. 401 travels over the southern edge of the field. Now, the interesting thing about this field is if these black diamonds are active or abandoned, mainly active gas wells, and there's about 130 existing or abandoned wells into this Cambrian gas reservoir. Now, if you're going to take an existing depleted field and turn it into an operating reservoir, whether it's for compressed air energy storage, or whether it's for CO2 or whatever you want to put into it, under pressure, and bring the pressure back up to 8 or 9 megapascals, most of those wells are going to have to be plugged and abandoned. And that is going to be a costly endeavor. I've done some polling of folks within the Ontario Petroleum Institute and within Enbridge, and we generally come to a number of around about 200,000 per well to plug each of those wells. So if you develop a depleted oil and gas field, you start off with a significant upfront liability of 25, 30 million maybe that you're going to have to pay. That isn't huge in terms of the costs we're dealing with in developing carbon sequestration, but it is significant. Now let's look at another area, the area of Haldimand, Norfolk. You can see Lake Erie down here. This is Turkey Point. Nanticoke is right in here, and Brantford is here. Here's Hamilton up here in the northeast corner of this figure. Now, this is interesting because we are close to Hamilton and Nanticoke, two steel sector emitters, and this is only about 80 kilometers between Hamilton and Nanticoke, and there are existing pipelines that Enbridge operate, a crude oil pipeline to the Imperial Oil refinery there, and a natural gas pipeline to the Stelco steel mill. And this is not so far from other emitters in the province. This is the cross section, just in case you missed that. There's the cross section here from Nanticoke up to Brantford and a bit beyond. This figure again is vertically exaggerated. On the left, on the ordinate here, the y-axis, you can see depth. This is meters above sea level, so minus 900, minus 800, 800 meters below sea level. Add another 200 meters of ground above sea level to the ground surface, and this is about a kilometer depth here, 1,000 meters below ground surface. Here's our Precambrian basement. After a few meters, it gets quite impermeable. And here's our Cambrian sandstone here. And everything above that, and we're not showing all the shallow geology here. We're starting off at 300 meters below sea level, so about 500 meters depth. This thickness of Ordovician argillaceous limestones and shales is essentially a cap rock. And it is 200 or 300 meters of very tight rock. So this makes the Cambrian here an excellent place in which to inject carbon dioxide. The carbon dioxide, as Maurice was saying, is buoyant, so it's going to move up dip along the bottom of the cap rock here. That means it'll move inland. We're going to need to know a good deal about the geology of the rock itself, the petrography of the rock. What do the pores look like? In other words, in the field, we'll measure injection rates, and we'll want to be able to correlate them with pore structure when we look at cores in the laboratory or in the Oil, Gas and Salt Resources Library down in London. So we're going to need to be able to correlate field measurements of injectivity with understanding what the pore structure looks like, whether it is in white light or UV light. This is showing a little bit of oil left in this porous sandstone. This is the Cambrian sandstones from down in Kent County. We're also going to need to undertake what is known as MMV, Measurement, Monitoring and Verification. Unfortunately, we have the services of Scott Mundell at Windsor, who's been conducting this kind of work for quite some time in Western Canada. And it will involve measuring the various carbon species, CO2, methane, not just their concentration, but also their isotopic profile in various compartments: atmosphere, surface soil, subsurface, groundwater, commercially accessible zones in the subsurface, what these carbon species are like in the reservoir. And what we're trying to do is, should there be any CO2 or methane found at the ground surface, we can identify where it came from. And really, we're doing MMV to understand geochemical risks. This is illustrated 10 years ago out in Weyburn, Saskatchewan, where they have a large CO2 injection operation, CCS operation, that was run by using carbon dioxide from the Saskatchewan coal-fired plant. And 10 years ago, there were allegations by a farmer or farmers that there seemed to be CO2 leaks at the ground surface. And the question was, where does this CO2 come from? Well, it was only by doing this MMV work that Scott Mundell and his team, this is the publication here in the International Journal of Greenhouse Gas Control, soil investigation of alleged gas migration issue on a residential farm above the Weyburn-Midale CO2 EOR project. Scott led that project and was able to demonstrate that this wasn't CO2 coming up from the Cambrian sandstone, the Deadwood sandstone out in Saskatchewan. It was actually natural CO2 that was present in the shallow soils. We also do MMV to detect geomechanical effects. And we do it for similar reasons. We do it for geochemistry, it is for performance assurance, regulatory compliance, public assurance, and risk reduction. We do need help from the provincial government, from the regulators. We do need a clarification of quite what we're going to be allowed to do. Present moment, it seems that the kind of project in Weyburn would not be permitted here in southwestern Ontario, that is CO2 injection for enhanced oil recovery. That's okay, we're not interested in doing that. In fact, any oil or residual gas in the ground surface is more a nuisance to us than anything else. But we do need to understand the legality of what the mineral rights mean with respect to the pore volume. In short, who owns the pore volume? And that is critical to us because it is, the legal structure is different in Eastern Canada than it is in the Western Canada Sedimentary Basin, because we have freeholders here and we need to understand how the rights to the pore volume are held. Also, we expect that the provincial government will be doing independent monitoring to assure that the public, that safe practices are being used. And finally, we're going to need help from the Ontario Geological Survey, which is based in Sudbury. Perhaps the first thing they might do is just hold a workshop, perhaps like this, on what is known about the Cambrian in southwestern Ontario. Hold it in London, perhaps with the OGSL. We also need the Ontario Geological Survey to share in the burden of drilling and exploring the Cambrian. It should not just be up to Shell and Enbridge and Stelco and others to be exploring the geology of southwestern Ontario. OGS did a really splendid job characterizing the Silurian aquifer in southwestern Ontario 10 years ago, between 2010 and 2015. And we need a repeat of that now, but for deeper, for the Cambrian aquifer. We need to know what the formation pressures and the groundwater quality are. So we have a series of objectives over the next 3 years, mainly getting started, understanding the system, and as I say, we hope to do that with OGS. We need to undertake the necessary field and laboratory testing and pilot test CO2 at selected sites. We need to develop robust designs for CO2 injection by numerical simulation and risk assessment. We need to select the carbon capture technologies that we will need to use. And as Eric Croiset said earlier, we're assuming we're going to be using chemical absorption, amine absorption, and so on. We need to undertake R&D into the sealing of existing active and abandoned wells, oil and gas wells in southwestern Ontario. This is going to be critical because we don't want to be injecting CO2 and it start displacing brine or natural gas or something else, CO2, as we inject. And we really need to be doing all this decade. We've got about 8 years to start injecting CO2 if it is to count in the 2030 CO2 census. In other words, the end of 2029, we've got to be injecting CO2 into the ground for it to be counted against the Prime Minister's pledge of 40% reduction. So we've got 8 years from today to achieve our goal. That's an awfully short time because estimates typically of characterizing saline aquifers are 5 to 10 years. Well, we're going to have to do it very, very rapidly. Now, we have been here before, as Dave Ryan mentioned, and that was in 2008. Andrew Hewitt of the Ministry of Natural Resources gave a very good description of the problem. When the problem was coal-fired power plants, this was before the McGuinty government shuttered the coal-fired power plants in Ontario. And the discussion was mainly about them. But, let's see, 2008. And the year before, Terry Carter and some colleagues had done a survey of sequestration in southern Ontario. Unfortunately, the ball was then dropped. It may have had something to do with the closing of the coal-fired power plants. There are rumors as to why this was dropped, but the federal government at the time didn't pursue this either. So all links with the American CCS community tended to be atrophied. We can't allow this to happen again because there are international pressures on industry that are now developing that will institute border tariff adjustments. So we cannot just go our own way here in Canada. We really have to start considering carbon capture, transportation, and sequestration very, very seriously in the next 6 months. through to 2030 and then beyond to 2050. Thanks very much indeed for your time. I think what we'll do is we'll break for lunch. Lunch is ready at the back, and sorry I've kept you as long as we have. We'll begin again at 1 o'clock. So now we're going to finish up the workshop with a couple of talks and Claudio's farewell. The first talk is going to be by my colleague Robert Walsh, who's a senior numerical modeler with Geotherma and has been working for quite a long time with Enbridge on the storage of natural gas in southwestern Ontario. And he's going to talk more about the specifics of how we would screen potential carbon dioxide sequestration reservoirs, how we would screen them for suitability, because there is so little known about the saline aquifers as opposed to the depleted oil and gas fields. There is so little known that we need to have a relatively inexpensive and short screening process which involves drilling and hydraulic testing. So, Robert, if you wouldn't mind coming forward.
Thanks, Dick. Good, I'm up. Yeah, so good afternoon. Is this interacting somehow? Thanks for the opportunity to present some of our ideas here today. As Dick said, I'm Robert Walsh, a senior engineer at Geotherma. As an organization, we've been working in the geological isolation business in Ontario for many years. We focus on a lot of our work on radioactive waste isolation and, as Dick said, on underground natural gas storage, working a lot with Enbridge. Today I'm going to describe an approach to assessing the carbon sequestration potential of Ontario's deep saline aquifers. I apologize now, there'll probably be a little bit of overlap with earlier talks, but yeah, so I'll try to make it not too unspeakably dull here today. And like I said, or like Dick said, focus on kind of initial screening. So I'm leaving out a lot of steps, but a lot of them have been covered. Oh yeah, for people who've worked with Geotherma for a while, you might not recognize, well, that's a new logo. We got a company to redesign our website a little while ago, and they said, your logo is ugly, can we give you a new one? And so when the creative people tell you your logo is ugly, you have to listen. So yeah, that's I decided to use that. Although our old website's still there, so you'll find that we have an ugly logo if you go to our website. Yeah. So what makes a suitable site? Now this is definitely a little bit repetitive, but I'll just go through it quickly. So there are some important constraints, and these can be summarized as injectivity, capacity, and isolation. By injectivity, as you've heard before, we mean the ability to inject CO2 into the formation at a sufficient rate without raising bottom hole pressure to a level that would fracture the formation, essentially. Or more accurately, we can't raise that bottom hole pressure to a level where we would exceed a regulatory criterion. The so-called delta pressure gradient. Capacity refers to then just the gross volumetric capacity of the formation, or how much CO2 we can reasonably or safely store in the formation. And then you start to think about pressures at a greater distance as well, as Maurice has talked about. And then finally, geological isolation refers to the ability of the formation and the overlying confining units to isolate the CO2 from other formations, from aquifers, and from the atmosphere for a very long time. when you consider isolation, in addition to looking at the mechanical and petrophysical properties of the cap rock, we have to consider the presence of faults, as has been discussed, and the potential for leakage through legacy well bores or abandoned wells. So those have to also be considered. And of course, there are other constraints. For instance, proximity to CO2 producers, and so on. But these topics have been covered by others, and we're going to focus on the geology here today, because if the rock ain't right, we ain't got a site. That's my slogan now. Dick talked about the injectivity index, and it's kind of a useful, at least for a point of discussion. So that's the ratio of your injection rate divided by delta pressure. And so once again, the difference between your bottom hole pressure during injection and the natural formation pressure. And it's a function of both the injectivity and capacity, really. And Valerie et al. In 2020 showed that it correlates with this, this permeability and thickness product. So I advanced further than I wanted to, but anyway. These are measured values from other projects. Dick showed this already in Cambrian sandstone in North America. And these are very preliminary estimates for a couple of proposed sites in Ontario. Very preliminary. We don't know a lot about them. I put error bounds on that, but that's really only the error of the correlation between permeability thickness and injectivity index. When you consider property or parameter uncertainty, you could say that our real error bounds. So yeah, that's the true extent of our uncertainty. So this site could be way up here. We really don't know. So putting it mildly, currently we know very little about the potential feasibility of these sites or other sites in southern Ontario. So then the question becomes, how do we reduce this uncertainty? So here's a flow chart that I put together. It's kind of a proposed process for geological and engineering characterization. It's a multi-stage process, potentially iterative. I've made it a little simpler than it really is. Given the limited information that we currently have for most of these formations, we have to proceed cautiously. And so if we refer back to injectivity, capacity, and isolation, the easiest to assess is likely injectivity, although you could argue capacity, you can think about that too pretty early in the process. So after we do a review, and we kind of look around, we check what data is available, we select some potential sites where we think maybe we can do this. The first stage in our assessment really has to be drilling and testing. And the reason for this is to find out if the target formation has sufficient injectivity, and that you can find out pretty quickly. I guess I would argue that there's no point in proceeding to baseline data collection, wider spread drilling, new 3D seismic, pilot scale, CO2 injection testing. We shouldn't do any of that until we know at least we've got some injectivity. So that's really our first hurdle that we have to get over. And so I'm going to focus today on kind of an initial site assessment rather than looking at everything here. Really on this very early part of the process is what I'm looking at here. So if we make that, now that's that orange box, and I've expanded and added more detail. So this shows kind of a possible workflow for initial site screening. The first stage is a review of all the available knowledge pertaining to the target reservoir and site, followed by drilling at least one borehole, a comprehensive testing program, interpretation of the data, including by modeling, and finally an assessment of the potential of the site. And I'll go through these in a little more detail. This process mirrors what we've previously done for assessments of natural gas storage reservoirs, or the process we're currently undertaking for geological characterization of a potential rad waste disposal site. The primary difference, well, it's not identical, and I think here we have the big difference of in those cases, we're really most interested in the impermeable formations and showing that they're impermeable enough. But here we also need to look at, of course, the permeable storage reservoir, which we don't know much about either. And if we determine at an early stage that it does not possess sufficient injectivity, there's little point in proceeding with additional measurements. So it's a little bit different in that sense. But let's go through these in a little bit more detail. So data review. I'll just run through this really quickly for those who don't do this every day. We're going to be looking at all available and relevant geological and engineering data. We can look at existing boreholes, and it was the guys at the OGSRL talked about this already. These well tickets from existing boreholes describe the stratigraphic sequence, obviously. They may also include borehole geophysical logs, fluid shows, pressure records from those fluid shows, fluid composition analysis if you're lucky, and plugging records. So all very useful information. In some locations, maybe there'll be some existing 2D or 3D seismic surveys, and maybe they need to be reanalyzed, but they may provide information on geological structure, faulting, the presence of traps. It just tells us more. Maybe there's previous property measurements in the same formations within the basin. I think we already know there isn't much for the Cambrian, but at least it gives us an indication of what to expect. This here is not Cambrian. Unfortunately, it's Bass Islands dolomite in Michigan, but it's at the same depth. Finally, much of this data has already been synthesized into conceptual geological models and hydrostratigraphic frameworks, and that's what the people at OGSRL and Ontario Geological Survey and places like that, they're working on these things, and we can use all that work that's been done to provide further insight into geological structure, formation thickness, fault locations, pinch outs, and other features of the geological system. Also not mentioned here, but previous measurements of in situ rock stress and regional stress mapping is another factor that should be considered at this stage. And yeah, this forms the starting point. And the next thing we should do is drilling and coring. So we've selected a promising site in terms of known geological properties and structure, which may not be much in terms of the properties. And hopefully it's near some concentrated sources of CO2. And we want to drill at least one borehole. We would want to core the immediate cap rock. Above that, we don't need to core at all. And of course, we want to core the target CO2 sequestration formation to take samples of that rock, should we want to test it further. So to access real data on the ground, there's no substitute for drilling. We can go quickly through the shallower rock. We can just go through it with rotary drilling. We don't need to recover core from really shallow areas. The cap rock we want, the target sequestration formation, we should core it even if we don't know yet that it's going to be good. Once we've drilled our hole, we will go on to the next stage. So drilling rig, this is our core processing facility. Right now we're drilling in the South Bruce area, and that's where we photograph the core and package it and log it and all that stuff. And that's just some core. This is Ordovician cap rock from southern Ontario, similar to what we might see at one of these proposed sites. And you can see there's writing all over it, and all sorts of thought has gone into that box of rocks before this picture was taken. While drilling, another thing we should consider is water sampling. And it sounds easy, but actually sampling water while you're drilling is bit of a process, but it's probably a good idea to do that to at least get water samples from permeable formations encountered during drilling to help establish baseline water composition in both the target formation and in shallower formations prior to CO2 injection. Particularly if some of these formations have really poor quality water, you want to establish, before you start messing with it, that stuff is naturally really bad water. It's not us. We are drilling into the water in on this project, we ran into some really stinky, horrible stuff, but it's not, it's polluted, but nature did it. Yeah, so once we've done that, we should test this hole. We should do some in situ testing, and the first thing we should do is hydraulic testing of the reservoir itself. Although, actually, no. Before that, we should do borehole geophysics, because nobody's going to let you put their tool down the hole until you've done geophysics, because it might get stuck. So borehole geophysics, that's some geophysical well logging results there. Run through it really quickly, but you can use it to identify your stratigraphic units again. You can use it to estimate formation density and thereby porosity. Caliper logs, be it physical calipers, if they have at least 4 arms, or acoustic calipers can provide information about borehole conditions, but they can also provide information on orientation and ratio of the horizontal principal stresses, and potentially provide information on stress magnitudes. Once you've done your logging, you've got all that interesting information. We want to do hydraulic testing of the target storage formation using water. I don't think we need to go straight to CO2. Probably test it with brine first. So a series of well-designed, single well injection tests could provide, or will provide, very accurate estimates of the permeability of these formations. That in turn can be used to estimate the injectivity index, which we've discussed. This will provide the first key piece of information about the potential sequestration reservoir. One point to bring up is that prior to doing this, we should definitely it's called developing the hole. So when you're drilling, even if you're not using mud, a lot of fines might go in and clog up these permeable formations. So you could test it, and then you'd be like, oh, this is terrible. We have no permeability. But that's just because you've clogged the area around the borehole. So we have to make sure we develop those, develop the sand face, and yeah. This actually can be achieved as a byproduct of the water sampling that I mentioned earlier. And of course, if results are promising, we should proceed with further in situ testing of the cap rock by hydraulic testing. And we'll have all those core samples, and at this point it would make sense to send those to labs for further testing. Laboratories will give you all sorts of useful information. So we'll get rock properties, including mineralogy, which is important when you start to think about the interaction of the CO2 with the native minerals. Porosity, it's an important consideration if you're thinking about the capacity and heterogeneity. Permeability, you can get permeability of the core as well as getting permeability through a larger test. Capillarity or pore size distributions. Thanks, Bruce Hart. I stole this off him. Yeah. Geomechanical testing. This is a picture from our friends at CanMet, where they've instrumented a little piece of rock and are now proceeding to smash it. So all very useful information. So once you've done all that, you've gathered all this information, now you can start thinking about better understanding the site. And so a natural next step might be numerical modeling. Maybe Steve knows. Can you recognize that by its shape, Steve? Running out of time? Okay. I'm already running out of time? Okay. Sorry, guys. So numerical modeling can tell you a lot. lots of different things you can look at. And here is a, come on, quick and dirty. Call this a very simplified back of the envelope numerical model for carbon injection into the Cambrian sandstone near Sarnia. These results are for illustrative purposes only and should not be considered definitive or even accurate. Okay, this is just for fun. So here's day one. We started injecting 1,000 tons per day. It's all full of water. 30 days later, we've got some CO2, we've got pressures proceeding well ahead of the plume, and after 120 days, and then after 365 days. And so you can see the buoyancy effect of CO2 is rising to the top of this. You can see that out here we've got a megapascal of delta pressure. That's the pressure increase above the background sort of formation pressure. But the majority of the CO2, even after all that time, is still kind of within 100 meters. Yeah, I'm not going to say too much more because I've run out of time apparently. But if we look at the same data, now these are just at different radial distances from the well. You can see the pressure rise, and these are kind of an estimated minimal principal stress and an estimated regulatory limit. And we're at this rate anyway, we're at 1,000 tons per day. The model is predicting a pressure increase still far below the estimated regulatory limit. And but I would caution that this is a very preliminary calculation, just for illustration purposes. Flipping to the next. Now we've done all that, and we can make our assessment of, do we proceed? Do we give up and go drill somewhere else? Or do we start injecting CO2 and see what happens? Finally, so there are relatively few measurements in the Cambrian. So to assess the feasibility of CO2 sequestration at selected sites, the first thing we need to do is drill and test the formations to establish injectivity, capacity, and isolation sequentially in that order. An alternative, this is the succinct alternative conclusion. There you go. Anyway, thanks to my colleagues and co-authors, and thank you for your attention, and sorry for going too long.
Thank you, Robert. I didn't know quite how Sarah Palin got into this presentation, but next, our penultimate speaker is Robin Hughes, who's going to talk about the general prospects for an Ontario carbon grid and CCS hubs. Robin, are you? Yes, he's there.
I'm all ready to go. Waiting for my presentation to come up here. So what I'm going to do is I'm going to try to show you a vision of what perhaps the CCUS network in Ontario is going to look like in, say, 10 to 15 years. And I think what I'm going to try to do is I'm going to go and talk about some of the risks that were discussed today and give some ideas about how we can mitigate some of the risks and actually accelerate timelines to start first movers to actually start capturing CO2 in advance of the 2029 deadline that was discussed. Next slide, please. So here's an overview of Ontario's emitters. We've seen this a few times today. Obviously, you've got this big cluster along the Lake Erie and Lake Ontario, and there's some fairly large emitters further north. Those look like they're isolated, but one of the things I'm going to do today is I'm going to show how they're not as isolated as they first appear, and how we can actually capture a very substantial portion of the emissions in Ontario without getting into extensive pipelining. And also, I'm going to show where we can tie in our pipelines to other jurisdictions in order to increase the robustness and flexibility of our CCS network within the province. And hopefully one thing we can also do is look at how we can tie in some of the negative emission sources through bioenergy CCS and further north, and understand how we can actually get what right now is sitting on Canadian Shield towards CO2 reservoirs further south. Next slide, please. So I think one thing I'd like to point out is that distance between Sarnia and Hamilton right now is essentially the same as the Alberta Carbon Trunk Line that is operating right now and collecting CO2 at fairly substantial quantities. It's got more capacity than it's currently operating with by quite a bit, but what it does is it shows us that at the scales we're talking, Alberta's beat us to it, and we don't like that. And honestly, this is not actually a terribly big deal. What we have to do is get together, plan what we're going to do, and start building this transportation network. And the questions are, obviously, we've gone through what's available in Ontario. Dave Ryan this morning mentioned that there's some really good locations in the Michigan Basin, and in fact, there are what can consider to be very low injectivity costs in that region. South of us in Ohio, there's some nice fields as well where we could potentially be using EOR or gas extraction. Now, obviously, that's not great for net zeros objectives, but there's also saline aquifers in New York State, Pennsylvania that would make use of. Also, one other thing we can consider is going, within Canada but out of province, and so those are longer pipelines, and I don't think those would actually proceed until we've got a very substantial rate of CO2 capture within this area. Just a couple of words about how we actually transport CO2. With the long distance pipelines, there are fairly tight restrictions on things like oxygen content and water content. I'm talking down below 100 parts per million for the most part. And it's typically operated at between about, let's say, 12 and 22 MPa. The Alberta Carbon Trunk Line sitting at about 17 MPa, and Shell Quest is up towards 22 MPa. So they're fairly high pressures. And the reason for that is it's an economic balance between the number of compressor stations, the diameter of the piping, and so on. And rail and shipping, though, are done differently. Those are actually done at cryogenic conditions. So it depends on the individual system, but you might be talking about pressures of, say, 7 or 8 bar. There's a bit of a range where you can do that, and that depends on what temperature you actually want to sit yourself at. In the case of rail, you're looking at about 100 tons of CO2 per rail car. So if you get into a large unit train, then it is perhaps unreasonable, but it's not impossible to get up to scales of like 1 million tons a year of CO2 transported from a facility. But at that point, you're talking about a rail car every hour getting filled up. So you're probably above the limit of what you want to do with rail for a given facility. On the other hand, shipping looks like it's reasonable up to about 1 million ton or maybe a little bit more per year. One thing we're going to have to contend with in the Great Lakes, though, is winter happens, and some of these shipping lanes are actually shut down, say, between New Year's and March. There is a corridor from Port Colborne up to Sault Ste. Marie that remains open all year, but Lake Ontario and the lock system down to the Port of Montreal are often shut down in the winter, as are sections of Lake Superior. And next slide, please. So what you have here is the beginnings of a conceptual CO2 network for Ontario. And I'm just going to go through what the different line colors are and what they mean in sequence. The green lines are the existing oil and gas pipelines in the region. And I've taken this from Canvec data. There are additional pipelines not shown, but what shows up here is essentially the large transmission lines. So the ones that go over longer distances. And we're using that for our CCUS modeling framework to act as a proxy network for CO2 pipelines, as it's quite possible the cheapest way to move these things around is to use the existing rights of way. that are oil and gas now, or obviously we can also reuse the infrastructure for CO2 piping as well. The purple lines that we see are the existing railroad networks. And I haven't shown them, but there's obviously the shipping channels within the province as well. And what we're in the process of doing now is creating an integrated transportation network system between pipelines and rail and shipping that will optimize and minimize the cost of CO2 transport throughout the entire country, but specifically here within Ontario. Now you can see that there are some tie-ins to the United States there. There's one going in from Sarnia to central Michigan. There's one from the Sioux into northern Michigan. That particular one is located adjacent to an existing CO2 injection well. That was a test well that was drilled a number of years ago. And in both those cases, those are located on low-cost injection sites with very large capacity. So in both those cases, that is an attractive long-term location for us to be shipping CO2. Additionally, I've shown Interkip location there as well as Nanticoke. And then I've got a somewhat random placement of another site in New York State, but that's sitting on top of a saline aquifer that I don't have the data for. Instead of tying into the US ourselves and doing that optimization, I'm in communication with people that are doing work for the US Department of Energy to do the national CCS modeling for the entire United States too. And what the plan is for us to actually provide source nodes in their models so that they can model CO2 transport from Canada into the United States. And the benefit to them is the toll costs then are lower for their pipelines. And so the costs, say, of moving CO2 from Detroit to central Michigan would actually go down. And so that's good for both of us. So there's good reasons for the people in Michigan and New York State and so on to actually talk to us. Now, one of the interesting things is going east. It's quite a long distance out to the offshore, say, Nova Scotia, Newfoundland, Labrador, but there's a really nice chain of emitters along that entire route. So the pipeline is not just going from Ontario, it's a continuous stream of collection systems all the way from, say, Sarnia right through to the offshore. Next slide, please. So I've drilled in here a little bit to take a look at Southwest Ontario specifically. We are now doing costing for these particular lines that are in gold. So those are examples of where CO2 pipelines might go. And there's obviously a number of different routes, and we're going to be optimizing which route is best. One of the things we need is discussions with pipeline operators to understand if there's constraints that we're not aware of yet, or opportunities as well. If you look into the Toronto region, you can see there's a whole bunch of emitters that are right inside the city. And those are locations where, you know, it probably doesn't make sense to try to pull high pressure CO2 pipelines into downtown Toronto, for example. But at the same time, those are all sitting on railroad networks. And so that might be a better way to actually pull the CO2 that's captured within the city out into the outlying regions. And then at some point in time, you can go directly with some processing into injection wells, or there's also the opportunity for transferring that to CO2 pipelines, or alternately to ship, because the rail cars and the ships are actually using CO2 in the same state. So just as a quick glance here, you can see just about all of the emitters in Southwest Ontario are sitting on either a pipeline right away or on a railroad. And the large emitters, I've got them all configured so that they're actually sitting on pipelines. So this might be an awful lot more achievable in a shorter time than we first thought. And I think what we need to do is think about, you know, who are going to be the first movers, who's going to be putting equipment in first. And with this type of transportation network, we have to think about the long term, not just who goes first, but who's going to go last and how things change over time. So our optimization models are actually periodic in nature, and we can put in data and assumptions for every year and look out as far as we want. Yeah, next slide, please. So this is just a little explanation about how we're actually going about this. We've adopted some code that was originally written at Los Alamos National Lab down in the US. and we've converted it to the Canadian context. So the overall objective is to minimize the CO2 transportation costs, including uncertainty. So there will be something along the lines of uncertainty analysis with perhaps Monte Carlo, so that we can actually understand the distribution of the minimum transportation costs and see, which one of these transportation networks actually makes most sense given the uncertainty of policy directions and profitability of companies under these situations and that sort of thing. And we'll obviously have a number of different source nodes that are the CO2 capture plants. And one of the interesting things we're doing within this project as well, and we just got this data recently, is understanding what the hydrogen requirements would be for heavy trucking along the 400 series highways. And subsequently, you can then say we would need hydrogen production facilities in certain locations, and then that would also get tied into this network. And we could look at scenarios like, okay, well, maybe the CO2 pipeline is adjusted based on supplying hydrogen to heavy trucking and to industry. And there's even a lot of municipalities considering hydrogen as a heating source. But I think the most important thing in all of this is the federal government obviously can't do this alone. And we really need the input from everybody in this workshop so that we can get the numbers right and we can actually get to an optimization that makes sense. And that's not just a matter of numbers, but it's also a matter of understanding, geopolitical and social complications in locating these things in different places. Next slide, please. So, the title of the talk was Prospects, and I guess I have a summary of them here. I think most of the CO2 emitted from large emitters in Ontario can be captured at relatively low costs. And most of these are not the high-cost CO2 capture systems that we hear about. This is not primarily, say, capture of CO2 from a natural gas combined cycle unit, though we have a few of them, where the costs are relatively high. Instead, we've kind of lucky in the fact that the industries we do have that are the large emitters, in fact, are on the low end of CO2 capture costs. And there are technologies available that can actually do the CO2 capture now, and it's fairly well understood. But even better news is there's a whole new suite of technologies that are just moving into demonstration now that have substantially lower cost CO2 capture. And I know some of the things we're working on now, we will not see an increase in cost for an end product due to CO2 capture if we adopt these new technologies. And that's because we're not just doing a Band-Aid solution to capturing the CO2 off the flue gas, but we're actually reinventing the way that process actually performs. And that's the most important thing to do, is make sure your process has the lowest emissions possible to start with. The second point is the majority of the emitters, you can see that in the lower picture there, is that most of the emitters are in a line between Sarnia and Kingston. So a pipeline is actually reasonably straightforward to route through there, though you've got to get around Toronto. Most of the smaller emitters have access to railroads, and so it's a good option for them. And the smaller emitters being captured is good for everybody because it's really important to have economies of scale in these systems, and the more CO2 you can move, the lower the toll costs are going to be for transport. And I think we've probably got about 3 million tons CO2 per year of emissions from CO2 biomass combustion right now, or bioenergy projects. And that can provide us with a negative emission source. And that's key to actually getting down to net zero. I haven't finalized the analysis here yet, but I think it's reasonable that we can look at 20 to 30 megatons per year of CCUS in Ontario. And in order to make that happen, really you do need to get moving on this right away. That's the slides I have for today. Thank you. Maybe I'll just explain what's going on here too. So this is some of the GIS images we've got for Sarnia region. So we're looking at Shell and Nova there. You can see the little green lines that I mentioned before are actually showing up in those photographs. So those are pipelines moving around those particular facilities. And then I've got my orange pipelines representing the conceptual network. So they're showing up in my squiggly lines, but also in the actual ArcGIS images. And we're tying into AMD, Stelco, and Burla as well as Carmoose in the Hamilton area. And then that other image down below is of Stelco and Imperial. Thank you.
Thank you again. Thank you again, Robin. And Dave up there in Ottawa. So we have now come to the end of our workshop. I do thank you all for participating, and I'm going to leave the closing statements to Claudio Canizares, the Executive Director of WISE.
Okay. All right, so we come to the end of the workshop, which I hope you found useful. Thank you for being here. Thanks for your presence, your input, contributions. Thank you to the faculty members who came up with the idea and the organization, the invitations, and thank you to the staff, to Armugan and Sana for all your help and all the logistical help to make this happen. Greatly appreciate it. I think this has been a great opportunity to interact and do some visioning on this particular scope of CCS. And just to rehash some of the introductory remarks that have been sort of repeated throughout this meeting, there's certain urgency in acting on this particular file because of what is coming down the pipe, right? So there's an issue of the need to reduce carbon emissions in the short term. I guess we're talking about 8 years. I was hoping that it would be 10, but it's only 8. And in that regard, I guess it's very important to start acting on all of these issues. And particularly the issue of Ontario is particularly relevant for these discussions because of the level of industrial emissions that are in this region, okay? And the opportunities as well, right? Now, these are the issues that have been discussed, addressed in this morning in terms of CCS sequestration, transportation, and storage. And I guess the dominant topic was sequestration and the opportunities that presents for the industry in Ontario and certainly for us academics to collaborate with you. Now, what is going back to the objectives of these workshop, right? What is the intention? The intention of the workshop, besides having a discussion, having a venue to interact, collaborate, and come up with ideas. At the end of the day, what we would like to accomplish, because there's no free lunch, not that the lunch was much, but nevertheless, I guess our interest as WISE, as University of Waterloo, as faculty members, is to basically establish ways of collaborating with industry, with government, and making this a reality, making this happen, right? At least at the starting point, and that's our intention. So we're interested certainly in research and development, but also a very important part of our mandate and our obligation as university folks, as academics, is training. And I think that's also quite relevant for industry and for government as well, right? Because you will have the people that you need to deploy and help you with all these developments and all this work that needs to be done. So, how do we accomplish this? So I just wanted to go over, with you briefly over the opportunities, the options that we have to collaborate. So the idea would be next steps would be to certainly work together in developing projects, proposals, grants to access this funding available through either provincial or federal government. I guess it's clear that the federal government is already putting money on the table, and I guess there are opportunities there that I understand they are already being sought, and there's already work on that. I understand Enbridge is working with some of the faculty members here to basically make a proposal to NRCan, CanMed in terms of the funding that is being allocated for this particular file, this particular problem. Okay, in that context, I guess what I wanted to highlight is the fact that with this collaboration, right, many issues can be addressed. One of them is certainly, and it was mentioned here in the discussions earlier, intellectual property, right? And Waterloo is particularly well suited, and here's being the sponsors of these the workshop and these discussions. I guess I'm going to now do some advertising for Waterloo. And in terms of the IP, I think we're particularly well suited for collaborations with industry, given the fact that basically the researchers, rather than university, own the IP, and there's certainly plenty of avenue for negotiation and discussions in that sense. Although, as Maurice already mentioned, IP is part of the issue, but also there's some urgency and the need for collaboration and openness to make this happen ASAP, because I guess we're already late. As it was clear, the message that I got from these learning that I had in all of these, which is not my area. Now, what are the opportunities? So, clear opportunities for collaboration besides NRCan. Funding, there's certainly opportunities for funding through the federal government agencies, particularly the NSERC Alliance, which basically can duplicate the funding that's been allocated by the industry, and it can be triplicated if we get involved with the Ontario government or the Ontario Centres for Innovation, which is a provincial government funding agency for research. And certainly training. A big important main part of all of this is training, so that has to be kept in mind as well. So, in that regard, I guess what we would like to let you know, besides these opportunities that they are there, is that you can reach certainly to us, the 4 faculty members who have been involved in these discussions today, directly, or interact with us directly with WISE. We'll be very happy to help you, the staff of WISE, myself included, to facilitate these discussions and support applications, proposals, and opportunities for funding for all of these initiatives. And with that said, I guess that's all I had to say. I don't know if Maurice, Richard, or any of the colleagues want to add anything to this. Otherwise, look forward to interacting with you guys, following up from the discussions, particular opportunities that may arise, and we're certainly happy and open for business. Okay, thank you.